Learn the fundamentals of neural networks from one of the most popular machine learning instructors, Dr. Radu. In this unique hands-on course, you'll learn core concepts and manually tweak network parameters to create a self-driving car. While this is phase 3 of his machine learning series, it's fine to start here. So let's get started.
I've been wanting to make this course for 6 years. I got the idea when Grant from 3 Blue 1 Brown posted his video on neural networks. The moment he said this.
One thought experiment that is at once fun and kind of horrifying is to imagine sitting down and setting all of these weights and biases by hand.
So welcome to my fun and horrifying new course where we'll play with neural networks inside this special playground I created. The goal is to teach the car how to drive, and we'll do that by manually changing the network parameters using the mouse wheel. We'll start with a simple network that just stops the car from going off-road and gradually increases complexity to teach the car different traffic rules as well. Dare I say, you don't need any prerequisites to start this course. I think the playground and the lessons do a good job explaining the math. I use human language and only introduce fancy terms so you know they exist, in case you find them elsewhere. But if I'm wrong and you still get confused, just ask in the comments or on Discord. Now, by changing these parameters manually, we'll understand exactly what the neural network does. This is really different because courses normally teach neural networks in a machine learning context, where they're automatically generated from data. That makes them work really well, but it becomes impossible to tell what they do exactly. It's why we call them black boxes. But I want you to understand what the neural network can do before I teach those complex algorithms for generating them. And the best way to understand, I think, is by playing with them like this. Now, this course is good for those starting with AI, but also those with some experience who want to understand things better. I've been working with machine learning for over 10 years now, and some things still surprise me. I think it's because training complex models is so easy nowadays. Just write a few lines of code and you're done. Makes us overconfident, thinking we know more than we do. I've seen many solutions that fall short, are overly complex, and use unnecessary resources. If you took my machine learning course, you know what I'm talking about. There we used a huge neural network to get the best results, but one with a fraction of the size could have good accuracy as well, and we could explain what that does. So I think there's real value in revisiting basics from time to time. Throughout the course, I'll give you homework assignments to improve your logic and deepen your understanding. I'll also give you a final challenge to teach the car how to race instead of following the rules nicely. I'll host a live stream event where I race against your AI cars, and there will be prizes. I just haven't figured out what those are yet. But stay tuned. And while you're designing your race car, I'll continue to teach how to code some things as well. For that part, you do need to know some math and JavaScript. This playlist can help with that. And we will continue the self-driving car project, so it's good to be somewhat familiar with it, but we'll mostly just add new functionality into it. So if you feel confident in your skills, take the last version from GitHub and try to follow along. What I'll teach then is how to implement Dijkstra's shortest path algorithm, so the car knows how to reach its destination. I'll also teach how to make the game mechanics. We'll control the main car, but the others will be AI. I'll show you how to monitor their progress and make the scoreboard. Now, this top view is not great when racing, I think. I'm really used to seeing things from the car's perspective. So I'll teach you how to code the camera sensor where we render what the car sees. This might be useful someday for object recognition, but for now, I just like it. And what I like even more is this view from behind the car. I'm going to teach you how to do that as well, and I'm not done. Controlling the car with the keyboard is not ideal. I'll teach you how to implement analog steering twice. First, by turning this into a mobile app and using the device orientation sensor to turn. I think it's better than using the keyboard, but I have an even better one. Using the camera, some basic image processing, and these blue wristbands, we're basically gonna become Iron Man. Oh yeah, and the sound, it's procedurally generated from scratch. All of this is just plain JavaScript, no libraries, like everything else on the channel. So you can learn all inner workings of a complex system like this. And all of this is AI. The new camera sensor, the path finding, the fancy controls using the smartphone, or this thing, image processing, augmented reality, they all make the system more intelligent. That's what I want you to get from this course. AI is often a combination of things, not just neural networks. And artificial intelligence is not the same as machine learning. Many people confuse the two. There's no machine learning in this course. Which reminds me, someday I'll teach you how to add machine learning into the system as well. But for that, we need data. So if you want to help, go to this link and race. Try to beat my time from there. If you make an account and do a good job, your name will appear there and others will see you racing next to them. That's actually me racing. I'm recording every move we do, so I can replay it like that. But don't worry about making mistakes. For machine learning, we need to teach the car what not to do as well. So mistakes are more than welcome. Excited? Great. Now get ready to put your neurons into overdrive. This is the playground. And look at the car. It's doing something. It's applying the so-called right-hand rule for solving mazes. So if you're inside a maze, put your right hand on the wall and you'll eventually get out of it. Most of them anyway. There are some mazes where it doesn't work, but we'll get to that later. Now just look at this. The car is exploring. It's going everywhere. And it's actually great. It's not easy to do this. You can press this manual override button on the right, and now the car is controlled by the keys on the keyboard. And just try to use the arrow keys and make the car do the same things without crashing. It's really difficult, like a very tedious thing that you have to do. And if it happens so that you crash, then you can always press this other button here and the simulation will restart. So for me, this is quite challenging to get it to go even half as good as what this neural network can do. So turning off this manual override, you can see it's going much more confidently than me and knows how to turn just right. Now, let me put back on this manual override and teach you about the sensors next. So you can see these two lines coming out of the car. These are what I call sensors. And you can see what happens to this front sensor here when the car gets close to the border. It lights up. It's a proximity sensor. So it knows when something is nearby and how close that thing is. Now the sensor also has a range. So this tip here is as far as it's gonna read anything. And the values in that case are going to be 0. So now this front sensor doesn't read anything. And you can see these sensors as input values here to the network. And if you hover, the value is written there. So if I'm going to go now up here, you can see how that value is increasing from 0 to 1, essentially, or 100%. But not exactly 100%, because if I'm going to zoom here a little bit, you'll see that the sensor starts in the middle of the car. So it's not going to go all the way to 100% because the car is going to crash before that happens. So let's see where it crashed. It was at 93% or 0.93. Let's restart this simulation. And the other sensor is here on the right. And it's the second input to the matrix. And this one might actually go to 93%, maybe without crashing, because the car is not as wide as it is long. But I think soon after this 0.93 now, 0.94, okay. So it can go a little bit closer than the other one just because of how the car looks like. Let's restart this simulation. And even without hovering, you can see the intensity of these inputs. Like this one is colored yellow, this one is grayed out. It indicates that this one is reading a larger value. And see how this one is now lighting up as well. The last input here is a different kind of sensor. It's the speed of the car. In phase 1 of the self-driving car course, we only had these kind of sensors implemented via raycasting. But there are other things that the car can know, like it knows its speed. So this value here is going to have negative values when going backwards and positive values when going forward. So it's a little bit different than the other two sensors. It can also have negative values. The other ones couldn't have those. And look at the color coding. When I'm going backwards, that meter there is blue. And when I'm going forward, it's yellow. So this color coding, yellow for positive values and blue for negative values, is going to appear everywhere. So you can see here negative weights that are blue, and this is a positive weight. And here, this spinning bias value here is a positive value. This one here, you know it's a negative value because it's blue. And these up here are the outputs. So the car can go forward, left, right, and in reverse. And it only goes like that if these neurons light up. So these two are lighting up now. It means that the car would like to go forward and to the left, but because of this manual override is on, it doesn't do that. I don't let it do that. But it wants to do that. So let's see what happens if I move the car forward and that right sensor here doesn't read anything anymore. What happens to the outputs there? You can see it changed a little bit. It tries to go to the right now because it wants to look for that border, for that, that right-hand rule there. It looks for the border, so it's going to turn right. Let's see it do that. If I turn off this manual override, the car continues like that. And you can actually play with these values here on the right by using the mouse wheel. So, for example, you could change the value of this weight, maybe make it negative weight instead. And you can see that this is a very delicate system here. So the car doesn't work now as before anymore. But you could do that. The playground lets you play with these values any way you want. Like maybe let's make this bias also negative. It actually did something. It started working again, but then it crashed. So again, really sensitive. And I'm not going to explain to you what this network is doing right now. You will eventually understand what everything here is doing and be able to implement this logic for the right-hand rule and even the more complicated logic, like with the stop signs and traffic lights and things like that. You'll see. But we have to take things slow and step by step. So go to the top of the URL here where it says s is equal to default and type s is equal to FWD. And this here is a much simpler scenario from before. First, the car has only one sensor this time, this front-facing sensor here. But it works like before. So if I turn on this manual override and move the car forward, you can see that it's lighting up. And it also shows here as the input to the neural network. So this part is exactly the same as before, but only one input. And the network is really simple. It's just one neuron here making the decisions. And the only decision it can make is to go forward. We can control the car to do more than that. Like, we have access to all its capabilities here if I'm going to use the arrow keys, but this neural network can't decide all that. It only has the potential to go forward or not go forward. And at the moment, it's doing nothing. Like, if I'm going to turn off manual override, the car just stands still. This neuron is not lighting up. And the reason for that is how this thing works. So this input value coming from the sensor here, we can call this x. It's a variable. This value is multiplied by the weight. In this case, it's 0. And then if this value, x times this weight, is greater than the bias here, which is also 0, then this neuron lights up. But it can't be greater than the bias because this is 0 here. So any value for x multiplied by 0, it's going to be 0. And 0 is not greater than 0. So with this neural network here, it can never light up, no matter what the input says. We could make it light up by lowering the bias here. For example, let's make it minus 0.1, it crashed there. But basically any value here that is negative is going to work, and 0 or any positive value for the bias is not going to turn this network on ever, because the result of x times w here is always 0 because w is 0. So let's just leave this bias to something like minus 0.2 and restart the simulation and see the car going forward like that. It never stops now, okay? Because again, no matter what the value for x here, it's never going to be anything else than 0 when multiplied by 0. So this also needs to be something for it to work. And let's turn on manual override and restart and go somewhere up here with the car. For example, this location. And let's try to modify this weight so that this neuron turns off, because we want the car to stop going forward when it sees something so that it doesn't crash. You can try playing with this weight and having large values like this, and you'll see that nothing happens. This output neuron still says go forward. But if you go lower values, negative values, minus 0.2, 0.3, 4, 5, 6, minus 0.6 in this case, then this neuron turned off. And if I'm going to move the car a little bit here, you can see that there is this kind of sweet spot there where this neuron turns on and off. Let's restart this simulation and turn off the manual override, and the car still hits that place. So we need a different value for W. Let's put back manual override, restart, and let's try to get maybe somewhere here so that when we are further away, it turns off. So I'm going to modify now this weight and go lower. Looks like minus 0.8 is a value. But we can go actually even lower than this. So maybe minus 0.9, minus 1. And let's see what the result is here. You can see now this sweet spot is much lower here. Let's try to see what happens now. So restart this simulation and turn off the manual override. And it stopped. It didn't crash anymore. It stopped exactly at this dotted line here. Nice. So let's turn back on the manual override, restart, and see where is the spot where it changes. So here, this is the moment where it changes from on to off. And if you look at the input value, this 0, 19, and play a little bit with the car at that point, you will see that it changes at 20, basically. This 20 is the same value as here, but minus 20 in this case. And it's clear why that is if you look at this weight value, because it's just minus 1. So whatever x is, multiplied by minus 1 means minus x has to be greater than minus 0.2, or x less than 0.2, because the sign switches if you multiply by a negative value. So that's why these values are matching right now, because this weight is 1, minus 1, but basically it doesn't have any scaling effect other than flipping the sign. So having weights of 1 or minus 1 are making the math easier in a way. But basically what this means is that if x is going to be less than 20%, then this neuron stays on. Otherwise, the neuron stays off. Now, there is a way to visualize things so that we don't have to do this kind of mental math all the time. I'll show you. You just go here in the title and say s is equal to fwd underscore d. And it's the same thing as before. If you will turn off the manual override, you will see that the car is going to stop at this dotted line. But now this thing appears here at the bottom. This axis here is the same thing that we are visualizing here and here. So 0.79, or the 79%, it means 79% of this arrow. That's where this yellow dot is present. So this arrow is for the input value. Changing back to manual override, you can see that I'm moving this point up and down because that's how the relationship with the sensor is changing. This point will always be in the positive side of this axis, because if we go far away like this, the smallest value that the sensor can read is 0, so it aligns like that. And there is also this other line here and this lighter region. This is controlled by the weight and the bias. The bias, if you're going to lower it, make it even smaller, it's going to move that region up. And increasing it is going to move that region down. Now we had it at minus 0.2. Let's keep this value. And let's see what happens when we modify the weight. Increasing it does this, and decreasing it does that. It changes the slope of that line. So this describes a line. And the lighter region that I have here, I made it so that when this yellow dot is inside of this lighter region, it means that this neuron turns on. So now if I'm going to move the car up a bit, you can see that that place where the lighter region intersects the axis is the same spot where the neuron turns on and off. So you can tell where that point is just visually. This is 20% of the whole distance here without doing any mental calculations. And this network that we have here that solves our problem is not the only one that solves our problem. Let me show you. You can put here a value of minus 0.1. And then this value, let's change it to minus 0.5. And you can see that this point lines up again. The difference now is that this slope right here decreases at a slower rate, at half the rate that the value on x is. And this network works exactly as before. So if I restart this and remove the manual override, you can see that the car is stopping exactly at the same spot. So there are two solutions for the problem. Now, homework task for you. Think about it. How many solutions are there really? Let me know in the comments. Let's do the math as well to confirm that this point here is at 20%. So x times minus 0.5 has to be equal to minus 0.1. So dividing by minus 0.5 means that x is equal to 1 divided by 5 basically, and that is 20%. And you could write this in code. You could make a simple if statement and say if minus 0.5 x, if the variable x is the input, is greater than minus 0.1, then accelerate. Otherwise, do nothing. So that piece of code is the same thing as what this neural network is doing. It's important to understand that the neural networks are capable of doing these kind of if statements. Now, there's one more thing I want to show you here. If you click on this diagram, it's going to show you a simplified view where it only uses one dimension. So these 2 dimensions here are important if you want to display this slope as well. So the simplified mode loses some information. We don't know what that slope is. But for understanding what happens here and seeing that the neuron is on when the sensor is reading in this section here, this is enough. And reducing from 2 dimensions to 1 dimension like this will mean that in the future we'll be able to show higher dimensions easier. So losing some information, but it will let us do some nice visualizations later on. Play around with these values again and see how the visualization changes there. Maybe we use the minus 0.2 value and the minus 1 weight, the one with the simple math from previously, and you see it still looks the same as before. But the slope now decreases much faster at the same rate as x. And what I mean by that is if I'm going to go here and put this bias to 0, whatever the value is here, it's going to be the same here. So this is essentially a square. Now, if this weight is going to decrease by 0.5, for example, then this rectangle here is not a square anymore. It actually fits 2 squares because the rate this decreases is half of this x. Now, believe it or not, I'm not done talking about just one output there. Next time, we'll still have only one output there, and there's a lot to talk about it. But I want to leave you with something more fun to do. So go here at the top and say S is equal to BCK. And now you can practice having 2 outputs, going forward and backward, and see what you can do with that. Let me just show you something real quick. So here, this is the same as before. You can control this lighter grayish region, but the other is going to control this green region here. So if I'm going to increase this bias so that it goes like that and decrease this one, now the car is going to go backwards in the beginning. Your homework is going to be to make it go forward and then bounce back like that. People teach neural networks in different ways, and that can make things confusing. I'm going to try to clarify some things now. You don't really have to listen to this part. It won't matter in the rest of the lessons, but it might help you someday. Now, some people say that for the neuron to light up, x times the weight must be greater or equal to the bias. Not really a big change, but that neuron would light up now with everything set to 0, and in ours, it doesn't. But you can always make a small change to the bias and it's going to work pretty much the same. There's no real reason to choose one over the other, so you will find both implementations out there. Just don't be confused. Another thing people do is move the bias here, on the left. Same thing so far, but they also changed the minus to a plus. This doesn't seem right. I mean, it's not the same thing anymore. But again, it doesn't really matter. Any network you find that works in the first case can be transformed into one that works in the second case. Just flip the value of the bias. The reason you find this implementation is because it looks like the line equation, something people are familiar with. I like to use the neuron fires when stimulated above a threshold idea, so it's just personal preference. Another thing you may find is people removing the bias entirely, but that would break things. We saw earlier that we really need the bias. So for it to still work, they add here an extra weight connected to a fake node that is always on. So this weight here acts exactly like the bias. And everything is all right. I think people like this because it groups together all parameters in one thing, so to speak. Now, this here is called an activation function, and this one in particular is a step function. There are others that are more powerful, like a sigmoid here would produce values between 0 and 1, so the car could be more like in the real world and accelerate more or less depending on the situation. I don't want to teach smooth activation functions because our controls here are binary, and it would make things more complicated. Our car will still be able to control the speed by pressing the acceleration at different rates, so we don't really need those. But they are important when doing machine learning. A gradient like that helps optimize the networks. That's why you'll find them everywhere, like in this other playground I found while building mine. It's really great, a bit more abstract, but a really useful learning tool. So check that one out as well. We learned what one neuron can do with one input. Next, we'll see when one input is not enough. We'll try using 2 inputs and even a hidden layer. Prepare for some neurons in the shadows. Open the playground from the link in the description. It should have here fwd_g as the session name. Now let's have the same network as before. So minus 0.5 for the weight and minus 0.1 for the bias. And the car is going to stop right here at this dotted line. Let's change the objective so that it goes up as much as possible. So can we figure out a network that lets the car go as much as it can before hitting the border there? And we could try playing with this. Basically, it's kind of logical that this needs to be a little bit to the right. So maybe moving the bias like this. This might be too much. Let's try it. Too much. We probably need to change also this, maybe something like that. I don't know. Still too much. This is tedious. We can also do something else to figure it out. We can use the genetic algorithm from phase 1. It's right here. Let me show you. When it optimizes here, it's going to try to create many different cars simultaneously. And each of them have a different network. How different from the one we started with is controlled by this slider here. So if I'm going to go down all the way and press this button again, you will see apparently just one car going up, but it's actually 100 or whatever going up, and this network is the same that we were playing with before. Here in this simulation, when the car touches the border, it disappears entirely because there are many of them and I don't want it to be too crowded. So let's try to give a little bit of a mutation here. And that means that the network is going to be similar to the one before, but not exactly the same. So now you can see that we found a car that is pretty much touching the border, but it didn't disappear. It's still here. So it's a good car. And when we find a good car like this, we press this save button. And now we have this new car to work with. Like if we close this optimizer from here, you can see it going up and then stopping exactly there, pretty much. Let's see close. Is it really very close, or could it go even higher? It might go even higher a little bit. Let's try optimizing again. Let's save and try again. Every time we run this optimization, the previous best car is not lost. So if it looks good, saving in the worst case, it's just going to give us the same thing we have previously. We don't lose anything valuable like this. So let's save again. And the last time, I just want to be sure that I'm getting as good value as I can get there. Save. I think it looks kind of like as before, so maybe it was good the first time already. And these values, minus 0.56 and minus 0.14. Let's figure out what this value is here. Turning on the calculator, and 0.14 divided by 0.56. 0.25. So that seems to be the point here, 0.25. But this weight and bias are quite complicated. We already start to have now the second decimal there. And these are some things that we can expect from neural networks. They don't give us the easiest way to write 0.25 there. There are several easier ones that I can think of right off the bat. For example, here I could put minus 0.1. Now, if you press the 0 key on your keyboard, it's going to zero that, and lower like this, minus 0.1, and this could be minus 0.4. So zero that, minus 0.4. So this should be the same thing as before. Let's try to restart. And it is, but it's a simpler one because 1 divided by 4 is 25%. So easier for us to understand the values, but the end result is the same. There are other values here that are easy to understand, like minus 1 and minus 25. For these small values, when scrolling, hold down the Shift key. This is going to make you scroll more precisely like that. So refresh. And this one works as well. There are many solutions here. The one found by the genetic algorithm is just one of them. And these, for me at least, are easier to understand when I look at the numbers, what is really going on here. Now, it's important to stop and think, what is the car really learning here? What is this function for? And one thing that can help with that is changing here the title FWD_B. And we get the same thing, but now the car is a bus. And you can see it doesn't work. The reason why it doesn't work is that the bus is longer. So the distance here from the center of the sensor to the tip of the bus is longer than we had before. So it is going to touch. We could run the same optimizer again and find a solution that works for the bus. So that's no problem. But the same brain that we had previously doesn't work also for the bus and for the previous car that we had. Let's save this one and now close, and let's see the bus going smoothly, and it stopped perfectly there. But if we go back now, we can see that the car is stopping not anymore in the last moment where it could stop there, because it's using the brain that we made for the bus. So this is important, how big the car is. And in some cases, real life cases, people are making the same kind of cars equipped with the same kind of brains, and then they have different brains for other cars that are different, just because the car has a different size to it. If you want to have one brain that does everything, then the size of the car has to be an input here, an additional input. We won't be doing anything like that here. It's not very complicated, but I don't want to teach you about the buses here. I just want to focus on the cars. But basically, we need to be able to understand that a longer car needs to stop accelerating earlier than a shorter one. Now let's go back to these values here, -1 and -0.25, like this. Restart just to see that it works. And another thing that doesn't work is if you write here FWD_2. So we have the same car from previously, and it goes just as expected, but there's another car on the left, and both of them have the same brain. So, interestingly, the car on the left does nothing. Stop and try to figure out why. Maybe pause the video and think about it. I'm gonna start talking again in 5, 4, 3, 2, 1. So there are 2 dots here on the right. One is for the car on the right, the one that is moving, and the other one is outside of this region to begin with. So this car is so close that it's already inside of that black region where the neuron doesn't fire. So it's never going to start. If the car is too close there, it's never going to start. And you can really tell that something else is needed here. I mean, what happens if we do make this car move just like this? For example, we can lower this bias more, like that. It's moving, right? But if we restart the simulation, that means that this other car on the right is going to crash because it's going to stop accelerating much later. So we can't have them both, not with one input here. Let's see what happens if we introduce the speed as well. So here at the top, S is equal to SPD_2. And now we have some extra things here. We're going to get to them in a little bit. But first, let's just put some values for these weights and biases. Let's put -4 here, -0.4, and -0.4 here as well. And here, -0.3. And let's refresh. And something happens, and arguably it's better than before. It's not perfect. This car is not going all the way till the end. This one is also not going till the end. It's worse than the one on the right, but both of them move this time. So it looks like something. Now, before we get into what is happening here, I want to show you a nice tool. This Desmos calculator has a 3D version now. So desmos.com/3D here. And let's write the same function we had previously. So -0.4x -0.4y has to be greater than -0.3. And you can see a flat surface here. this red region in the XY plane. Now, just a little bit of exploring here. This is the same thing as if you write -0 for x, -0 for y, plus 0.3 greater than 0, right? So let's write that. Plus 0.3 greater than 0. It's exactly the same thing. We just moved that one term. Now, if we remove the greater than 0, we move out of the XY plane and we're in 3D now. We are defining a plane. This now, what we have here, is not defining a line anymore. It's defining a plane. And only when we do that kind of comparison, like equal to 0 means the line where that intersects the XY plane there, or greater than 0 means all the parts of this plane that are above water, so to speak. So positive values. Now this 0.3 here is called the z-intercept. It's actually this point right here where the plane is touching this z-axis. Because if x and y are 0 here, then you get just that. So that's why it's called the z-intercept. And this here controls the rate of decrease, in this case on the x, and this one the rate of decrease on the y. So this plane is tilted in the same way on x as it is on y. But if you would have here minus 0.8y, for example, it's going to be tilted on x less than it is tilted on y. It's much more tilted this way than this way. But let's go back to our original one. So minus 0.4y. And let's go here and have this XY orientation and zoom in a little bit because we are only interested in values between -1 and 1. Now, this is not centered really well. You can go to these settings here and say center origin. We can also make these surfaces translucent like that so we can see through it. Let's zoom out a bit so that this 1 appears here and -1 is here. So this, what you see here, is the same that what I am plotting here. I'm just using a little bit of shading here. So kind of like the plane going under the water there. You can see it like that. And there is a slider here at the bottom that actually controls how pixelated this image is. It takes effort, processing power to calculate this image right here. So I don't really recommend getting this smooth version from the left side, sticking to something like this and above if your computer starts to burn up. But basically this plane, where this plane is above the water, that's when this is going to trigger now. So if these dots appear to be on land, then that is going to trigger for them. And this mode also has a simplified view because this is showing a 3D space here, right? But we don't really care about what is going underwater. So if you click on this once, it's a simplified view showing just the part of the plane that is above water. Or you can consider it like that. So back to the 2D space coming after we have an inequality sign there. So let's rerun now the simulation and see what is happening here. It's very interesting, right? You should take a moment and try running this many times and paying close attention to what is really going on there. So this car on the left that is stopping early, it's this point. It's moving on the edge of this plane here and then somehow going down and stopping early. The other one, the car on the right, goes higher here and somehow slingshots away from this plane. Like it jumps from there, kind of. And it falls down later. Interesting, isn't it? Now, if you look at the top here, I can only show one of the two brains. They are the same brain, so the same value for this weight, the same value for that weight, and for the bias, but the inputs for them differ, because now this one is closer, so it has a larger value for this 0.86. This is 0.86 here. This is going to be smaller, right? So the brain that you see on the right here is going to be from this car here. And if you turn on manual override, you can see that brain changing while I'm moving that car. And look at what the point is doing on the right. So I'm moving the car forward and backwards and forward and backwards. And because I'm changing the speed like that, it kind of looks like it's drawing a circle, because it moves the point up and down, also below the 0 point vertically, because the speed can be negative in this case. But combined with the sensor there is also moving it from the left to right. So somehow it's drawing a circular pattern there. Of course, if you would do this somewhere below here where this doesn't read anything, then that point just moves up and down like that, because there is nothing moving it left to right. The sensor isn't picking up anything. And of course, if I'm stopped, then the point is just going to lie on the horizontal axis like that. So really, there is a lot going on here. And I recommend you play with this. It's really fun. But let's try to optimize this so that the cars go as much as possible. And let's use the optimizer from here. So hopefully we're going to get cars that are going to be as close as possible to the border there. And now we are getting something better, actually. So let's save this and let's try again. Now, one thing when doing this simulation, the cars, there are two sets of them, right? On the left and on the right. They have the same brains. What I mean here is that the cars here are all a little bit different, mutated slightly, but exactly the same brains from this set are copied in this set. And the car showing in red here is the best one of both sets. So you might see here a car that is a little bit better still in front of this one, and it didn't yet touch, but its counterpart from here, it's maybe below somehow. So the added distance that they traveled is less. Let's save and try one more time. Let's see if we can get it really, really close there. It's still doing something, so wait for it to stop before saving anything, otherwise it might collapse eventually. Let's save this, and I think I'm happy with this. It looks really good. Now let's close this and see just two individual cars. And it's nice, they are stopping there. And they are doing some kind of crazy things here. But if you're like me, something bugs you at this point. The car on the right actually seems to arrive faster than the car on the left, which doesn't make sense. I mean, look at this. It's overtaking it about now and stopping it. Let me show you that again. So it's overtaking it now and stopping there. And if you look here in the diagram, this one is slowly making its way there, and you can kind of see the overtaking moment from this slingshot guy that just lands there where it should be ending. So the fitness function described inside of this optimization is go as far as possible, but it doesn't say anything about the speed. Like, it doesn't matter if they are going there as fast as possible or not. And integrating both of those in a fitness function is not easy because it's a kind of a two-parameter optimization function. So we are just going to not use the optimizer anymore, but I do want to show you still this. Like, if we decrease this value even more, the rate of decrease on the speed here, it's going to move that plane kind of like that even more. So here, this apparent slope is going to go down like that. And refreshing now is going to make the cars start to do that even earlier. And now they have this really, really slow movement at the end here. You can go even further than that, like this. And now you see very soon they start doing that. And they start to really, really crawl there in a funny way. Of course, increasing this too much like this is a big problem, because this is going to make them slingshot like that really much. It makes them slingshot because they accumulate speed, and then the friction is not enough to slow them down on time. So there are very many things here to consider when doing this optimization, like how the slope should be here exactly. But the really important thing is this point right here where the car must stop. Let's refresh now. And we see that we got something good. So this point here is really important. It needs to be outside of this lighter region. So it shouldn't be on land, because if it is, then it's going to accelerate more, and that means that it's going to get so close that it collides. But now let's focus on the car on the right. Let's refresh, and it's this one. It's slingshotting. We kind of want it to slingshot more, right? So that it lands perfectly in that one spot. Could we do that? So I need this to be a little bit higher there. I think that's too much, so I'm going to hold shift and maybe say minus 35%. Too much. So let's try minus 38% on this one. It's now doing that thing. It's fixing it, getting close. So it should be a little bit higher, minus 0.37 maybe. Let's refresh. Still doing that. 36. And now it crashes there. So it's not easy to figure out the exact values. We would need even more decimals there. Or we could play with this value as well. Increasing this is going to lower this a little more. Okay, now it stops nicely without it triggering anymore. It could still go a little bit higher. So maybe this one we try to increase a little bit. Okay, this is perfect for me. But let's now focus on this other car. What is happening with that? So you can see it doesn't go as far. And it even moves a little bit after that one has stopped, so it's not as good. Let's see what happens here. It's sliding down like that, right? And you can see it's stopping before the other car, closer to this 0 here. So that means that the sensor is reading a smaller value here. So it's further away from the border. We could get closer to the border if we move this a little bit like that. So we could go here and make it higher, but hold down shift. So let's make 29, and you could see it moved a little bit forward. Let's try 28. And the one on the right is also moving now, and it's too much. It actually collides to the wall. So let's just stick to minus 0.29 and rerun this simulation. And this one got closer, but it's still not exactly there. And it's doing that thing where it's sliding down the hill instead of jumping somehow, slingshotting like that so that it lands perfectly there. Let me run this with a higher quality here just to show you better what is going on, because that pixelation is interfering a little bit. Basically, we would like there to still be some land here, so that this car can accelerate a little bit more and then slingshot exactly there. But there is a problem with that. You see, this other car needs this point here to be the border. So if that car needs that point to be the border, and the one on the left needs a point there, and this point here needs to be outside of that region, it's not possible to do this with one single line, is it? And that's where hidden layers come in. A hidden layer is a row like this where we can add more neurons. They're called hidden neurons or hidden nodes, if you prefer the graph terminology, because their computations are not usually seen from outside the black box. Now here we do see everything, but I still use the word hidden when I mean not an input or output node. More terminology. This is also called a perceptron. When we add hidden layers, it becomes a multi-layer perceptron. It's important to know this because some libraries use it. Like when we use neural networks in the machine learning course, we used the MLP classifier inside the scikit-learn library in Python. So good to know that means a neural network. Go up here and put underscore h instead of 2. Now go here and make sure that this pixelation is on, because we're going to change some things here and it's going to be slow otherwise. And let's do something. Click first on this point. And now you can actually create a new point here. And this one here, connect to the same one. So we created a new neuron here with these inputs. And let's add the same values here. So minus 0.29. I'm just going to go to minus 30 and then hold shift and go up one. And here minus 0.35. And 1, 2, 3, 4, 5, like this. And the bias here, minus 0.26. Like so. This neuron is the same as this one here. You're going to see if we rerun this simulation that both of them are going to blink exactly in the same way. Now we can actually remove these links by right-clicking on them. And this one. And let's move this one on the right. Click on it and connect it to the output. Now reset the bias here to 0. You can press 0 on your keyboard. And you can put any positive weight here. Anything will work. Because basically the value of this neuron here, when it's on, a value of 1, multiplied by any positive weight, is going to be greater than 0. So these now are in sync. I'll show you. We go here and refresh, and this is the same thing as before. You can see the same shape appearing here in this diagram. Now this solution here with these neurons works nice for the car on the right, but not for the one on the left. That's the one that we try to fix. So let's create a copy of this and try to modify it so that it works well for the car on the left. I'm just going to click on this and create a new neuron here. And same values, so minus 0.29, minus 0.35, and minus 0.26. So now if I'm going to connect this one up here, and let's set this weight to 0, and this one to 0.1 or anything positive, we get the same thing here. So just to test, this should work in the same way. The car on the right is stopping perfectly. The one on the left still has a little bit of work to do. Let's get this slope to go a little bit like that. So we're going to increase this value here slightly, so holding shift. And basically I want to get this other car here to slingshot. I don't care if this one breaks anymore. I just want this one to work. And it doesn't really work. It does slingshot a little bit, maybe until here, but it needs to be a little higher. Maybe 26. It's better, but still a little bit more. 24. Even more. Okay, so now it looks perfect. It stops perfect, but the other one breaks. So let's compare now the two functions, and I'm going to put back this high quality diagram here, and let me turn off this one and on the other one. Let's rerun the simulation and see where the car on the right jumps. It's this point right here. And now with the other one, let's see where the other one jumps. It's this point right here. Now turn on this pixelation more because it's really quite slow. And let's create another neuron where we try to define a line that touches both of those points. Let's set this one to 0, this one to some positive value. And here, let's try with this left one first, maybe minus 40, the one on the right, minus 90, And the bias here, let's say 60. And now I'm going to teach you how to do the conditional AND. So we want this one and this one to be on, because then this region will essentially intersect with this region, giving us a curve here, not a straight line. So to do that, we put both of these values like this, and you can already see a curve appearing here. But we don't want it like that. We want it at the intersection somehow. So now this is actually an OR, because it's either this one or this one. So we also learned how to do the conditional OR. But to do the AND, we are going to increase the bias here like that. So the value here, if it's on, then it's going to be multiplied by 0.1. So we have 0.1 from here. And if this is on, 0.1 from here. So adding these is going to be 0.2, which is greater than 0.1. But if only one of these is on, like now, then this doesn't turn on because it needs both of them to activate. So let's just try to see how this one works. Probably we need to do some fine-tuning. Yeah, looks like this car is crashing because this is too high. We need to lower it down a bit. So minus 92 maybe. If you look closely, what happens here, it touches that tip a little bit. You can see here, after it stops, it blinks a little bit. So I think that we need to also adjust that one slightly. So here where it says minus 0.40, let's make it maybe minus 0.43. Okay. I think this is perfect. And we don't need this one anymore because this is anyway connected to 0 here. It was just used as a reference. So let's remove it by right-clicking on this node, then it's going to remove all the other links as well. Now your homework. Go up here and say SPD_3. Try to get it to work for 3 cars. This one seems to be crashing at the moment. One quick note here. I've found many resources claiming you need smooth activation functions to have curves here. One of them in a lecture by a top university. Now, what I'm sure they meant was a smooth curve, because we got a curve here already using a step function. A curve just means something deviating from a straight path, doesn't necessarily have to be smooth. It may sound like a small thing, but I think that false information like that is confusing, especially because it seems like it should be true. So people pass it around a lot, and it makes understanding things harder, I think. The playground doesn't support smooth activation functions, and as I said earlier, we won't be studying them in this course. But if you're curious, that shouldn't stop you from learning. Nowadays, there are a bunch of resources that can help. It's lesson 3 and we're still using 1 output, but that's about to change. We'll start using 2 and then 4, so the network can tell the car to go forward, backward, left, or right. Now this is called a multi-label neural network. And you don't need to know this name to follow along, but I do want to tell some terminology, and don't confuse it with a multi-class neural network. A multi-class neural network is what we had in the machine learning course, where the drawing could be classified as one thing. But here, the network can say to go forward and left at the same time, for example. So it's a different thing. Okay, finally, the car will start exploring. Open the playground from the link in the description, and you're going to see this scenario with 3 cars. But the difference is that now we also have the possibility to go in reverse. And I'm going to show you how easy it is to solve this problem when we can do both of these things. I'm going to set this weight here to -1. This one also to -1. And up here, the bias -0.9, like this. Now, this by itself crashes 2 of the cars, but if we also go on the right here and put the weight of 1, and 0.9, essentially filling this remaining space, and restarting the simulation, see what happened? Let's check this again. It looks really good. The cars are stopping where they should, and they are slowing down only when they need to at the very end. This one arrives first, this second, this third. If you just look at what happens here, it looks all right. And we don't have any curves or any fancy things, but what we do have is this other ability of the car to slow down quicker. So even if you could see a little bit of that kind of bouncing effect here, only for the fastest moving car, I don't know if you can even notice it. It's not a big deal anymore because this is such a powerful maneuver that it's basically making all of these points just follow this line separating the 2 surfaces here. And at the very end, you can see these things blinking like crazy because we're at the edge. This is a bit annoying here if you look at the neural network, but if you look here on the left, even if you zoom in, the cars don't really move because the acceleration is so small there and going in both directions. So I'm not really bothered by it, but if you are, you could set, for example, this to -0.89, and now there will be a small gap there. Maybe if I'm going to do this, you can see this very narrow gap here forming where the points stabilize nicely. Now let me show you the next homework. Go to s equals to rev_h. It's going to be this same thing, but just 1 car in the middle. And the goal for you is to make it do this, where the car goes up and down like that forever. Try to find a network configuration that does that. I think it's pretty cool. But now we're going to move on and I'm going to teach you about steering. So let's change the link at the top to s equals to str_0. And you're going to see this new scenario here. And the car has one more sensor, the one on the right. You can see this extra input appearing here. And it's now sensing something because the road border is quite close. But the other 2 are 0 because the car is not moving and because this is not sensing anything. Now here at the top, there are 2 new outputs for turning left and for turning right. And all these weights connecting them. Now these are really confusing to work with like that, so let's remove them from this button right here and move things around to make things a little bit clearer. So let's separate this into 2 parts. 1 on the left here will be what we just did previously, going forward and being able to stop so we don't collide. And then on the right, let's keep the steering part. It's going to work with this new sensor that we have here. And let's do the same thing that we did before. So let's connect this one and say here -1, and this one -1, and here -0.9. And for the reverse, 1, 1, and 0.9. Now this is the same thing that we had before, and the car should stop nicely at the end. And it did. But if you look here, something strange happens. Focus on this diagram, and when we refresh, crazy things are going on. This doesn't look anything like what we had previously, right? And that's because here we don't have the speed now, we have this sensor. If you click on it, it's going to change to the speed and show what we had before exactly. So now you can recognize this pattern here. But what were we looking at before? So this is what you're gonna have to understand next. It looks like these regions are somehow changing, but they're not. You can only change those things if you play with the weights and biases from up there. What happens is that this is really a 3D space now. And one axis that goes like that is the speed in this case. It's the one that is missing from these two labels here. And what we are seeing here is a slice of the cube at that speed, somewhere inside of this cube, at the value of the current speed. So if I'm going to change to this, it's like we are watching the cube now from the top. And what we see when we change this, we see the cube from the side. So this amount of green that is still on the right of this point is actually the same in this case. But as the speed of the car changes, this amount of green that we see in this other view is going to start growing and then shrink back. Because here, as the point is moving up, if you think about some kind of horizontal line at that point location, the amount of green on that line is growing and then shrinking again. So growing and then shrinking again. So this is what we see in this view. Growing and then shrinking again. It's not easy. Maybe it's going to help if we use Desmos again. And let's type in the functions. So we have -1x, -x, -1y, -y, and there is no weight connected to z at the moment, so I'm just going to put +0z. And nothing appears here, and this is because what we are describing now is a hyperplane. It's something in 4 dimensions. And here Desmos is saying something. Try adding an equal sign to turn this into an equation, because it can't show 4 dimensions there. So you could put equals, like equals to our bias, which was -0.9. And this now turns into a plane in 3 dimensions. But we're really interested in the values that are above this bias, so greater than -0.9. So what we have now here is essentially the gray area in our diagram, but let's look at it from the top, like so. Let's make it actually gray. It's possible to do that here. And let's zoom in here so that we focus on the -1 +1 area. And let's add the green one next. So that was x plus y plus 0z. We are not using that at the moment. And this is greater than 0.9. And this is our green area. Let's make it green so it's similar to ours. And it looks pretty much the same as what we have here, looking from the top. But if we look from the side, like this, and slice the cube somehow. I'm not sure if we can do that. Let's try going here in the settings. Let's try putting here 0. Okay, it looks like we can. So 0 means that we are basically having a 0 speed now. And the car has a 0 speed at the moment. Let's turn on this manual override. And when I go in reverse, you see this green part disappears from here. It disappears from there because when you have a negative value for the speed, like -1 for example, then we are watching this part, this slice of the cube that doesn't have any green in it. But if we go forward and increase the speed, we get more green appearing there. And that's because we are slicing more in front there. Like, let's say 1 would be very much maximum speed of the car, but let's put 0.5 for example. So this is half as much as the maximum speed. And let's see if we can get to that if I start all the way at the bottom here. So let's see how much green is coming here. Yeah, I could get to that, but I don't want to crush the car. I really hope this is clear for you, because these things start to not be very easy to understand, and the tools can only do so much. Now let's think about turning. So I want to turn based on this sensor here. If it doesn't sense anything, or if nothing is close, if the border is not close here, I want the car to turn to the right. So I'm going to connect here this sensor, and to keep things easy, I'm just going to put -1 here, and now vertically I can move that red region as a percentage. So this 20%, -20% here just means 20% upwards here. So let's move this all the way to the top, maybe -0.9 like this. And it's still off because this dot is above it here. But if I'm going to move the car somewhere where this doesn't appear, then it's now moved in this red area. So this will make the car turn. And let's see how it goes. I'm going to remove this manual override, and the car is turning a bit too much and then crashes in the wall. So maybe a value of -0.8 is better. Let's try to restart. Okay. Yeah, it looks like we got it to turn, so it's really nice. And see what happens here in the diagram. So what did we add, this red region? Let's try adding it in Desmos as well. So this one doesn't depend on x at all. It's 0x plus 0y and minus z, because we have a -1 weight there, greater than -0.8. And we can change the color here to red, and this is what we get. Now, the option from here to have translucency, to see through these things, doesn't really work. When we have these solid objects, I think it shouldn't really work. It's kind of hard to think about these solid elements and seeing through them somehow. It's going to be very confusing anyway. But this didn't affect the other things. They are still there. If I'm going to toggle it from here, it's just a new thing that was added. So here you have a combination of green and red, really. And that combination of green and red is what I'm showing here as this orange when they are overlapping there. The gray and red makes the red appear brighter like this. But from here you can actually remove some of these elements if you find them confusing. Like if you just want to see the red area here, you can turn off the gray and you can see it now well, and the green, and you can focus on what happens with the point and in relation to this control here. But let's turn them back on and change this to the previous view and see what is happening. So you see this crazy blinking that is happening there? It's because the point goes inside the red region and outside of the red region, sometimes really, really quickly. Here, when it's actually doing the turn, it's doing that. So what happens is the point is basically somewhere at the border here and then moving like that really fast. That's what makes everything blink red when seen from this side here. Again, really hope you get it. Play with these things, it really helps, I think. Now, if you look at this, something is weird because the car is not really driving on its side of the road, it's driving in the middle like crazy. So let's try to do that. Probably what we need to do is decrease this value here. Let's try going slowly because minus 0.9 crashed it. So I'm just going to try 81, 82, and focus what happens on the car as I'm changing this. 83, you see it got closer. It got closer, 84. It's getting closer, but it's also sometimes moving on this kind of trajectory that is probably going to hit the wall eventually. Let's see, 86. Almost hit there. Let's try 87. Maybe this is as much as we can go. Okay. So at 87, this thing happened. Basically, it turned in a way that it was on a collision course. And we need to correct for that. If it gets too close to the side of the road, we have to teach it to turn left. So let's connect this here and do the opposite. So minus 1 turns to plus 1. And then here we have plus 87. Okay. And probably it helps to switch back into this other mode where we can see now this. So red and blue are the two different sides. If it's not going to turn right, it's going to turn left. And if we restart, we see the car correcting itself. It's actually doing it like crazy. If you see here, very quick corrections happening. And that's because there's no spacing here between the blue and the red. It also reminds me that in phase 1 of the course, some people were asking, why does the car shake like that? So now you have an answer. It was in between regions like this. Now it's better, it's on its side of the road, but it's touching that lane a little bit. I think we can do even better than that. So maybe let's try changing this to minus 0.9. Like so. And this one to 0.9. So forcing it even closer. I think this looks good. If this shaking bothers you, then you can always put here a higher value, like minus 0.89, and now the car is not going to correct itself as often. Let's see how it does in a different scenario. So change here to str_1. And now you see the car going in circles like that. And this is what I meant in the beginning, that the right-hand rule in mazes doesn't necessarily guarantee that you're gonna get out of the maze. You can also get stuck in situations like this. So I just wanted to show you a situation where it doesn't work. Let's move on to a more complex scenario, str_2. And see what happens here. Something kind of crazy happened there, right? Let's look at it a little bit more. So these things are quite nice. It's really keeping its lane. And then here, oh no. Oh, even crashing, horrible. So let's look again and see what happens. Here, this is fine, but here it's doing something crazy. And that's because the front sensor doesn't see anything when moving here, but it saw something when moving there, so it slowed the car down. This is the problem here as well. The front sensor doesn't see anything, so the car only sees that it has to turn right, but it has large speed. And the same thing happens here. Picks up speed even more, and then sees that it has to turn right, but then when the front sensor sees something, eventually it's too late for it to turn. Now, the solution for this is really to add more sensors, so that it can see things in front at different angles and figure out that something is coming. But I don't want to increase the complexity of this structure too much, because we will still add things to this, and it's going to become more and more confusing if we have more things to work with. What we will do is cap the speed, so that the car cannot go as fast as it can, but at the speed where this problem doesn't happen anymore. Think about it. The car sensing things on the right, really it finds out in the last minute that it has to turn. So if it's going some crazy speed there, it is going to fail. It's too late. So let's see how we cap the speed, and let's change here so that we see this chart, and let's remove blue and red because they are confusing. And let's remove these two links from here. We will do something else with the reverse section later. For now, it's best to focus just on this green area and cap it. So I want this section here to be black, so that the car doesn't accelerate to the speed that it could manage mechanically. And for that, I'm going to have to add here a new node like this. And let's just copy these values here. So -1, -1. And this one here is -0.9. And now these nodes are doing the same. So let's remove these links, put a 0 here. You can press 0 on your keyboard to do that faster. And let's connect these with some kind of positive weight, 0.1 for example. And you see this shape appearing here again. So now whatever this value is, this one is going to be the same. Now let's put this to 0 and create a new shape here that is just a horizontal flat line here and the bottom part gray. So I'm going to take the speed here only. It doesn't depend at all on this one, right? It's going to be a flat shape. And for simplicity, I like to put here -1. So here I can control a percentage. And let's try to put minus 0.4 and connect this one to the gray output and add some value there. So now this percentage here, if it's minus 0.5, it's exactly in the middle. This is higher, this is lower. Let's start at minus 0.5 and see if the car behavior changes. But we also have to do the combination. So the intersection between this region and this region, it's gonna keep just this kind of trapezoid here. To do AND, you put both of these to 0.1. And at the moment, this is actually doing OR, so it's either that or that. And here we can put 0.1. So that means that this needs to be on, this needs to be on for this one to activate. Great. And another homework for you would be to do the same thing for the green region. Here you would have to use OR, so it's a good chance to practice that logic. And you need to duplicate these, make similar logic, many complicated things, maybe clean this up a little bit, organize things differently, and connect in the same way to that one. Or do what I'm gonna do now and use the NOT operation. So what will happen is that when this one is on, this will be off. And when this one is off, this will be on, which kind of makes sense. I mean, when you drive a car, you typically accelerate or decelerate. You don't really let the car slow down by itself in almost any situation, unless you think about conserving gas or something like that. But if you want it to be fast, then you probably want to apply the brake if you are not accelerating. So having a NOT here does make some sense. And let's see how to do that. I'm going to create another node here. It's easiest to teach you like this. And let's copy these values now. So 0, 1, 0, 1, 0, 1. And remove these other links, right-clicking. And 0, this one, positive here. So these nodes are now in sync. We have the same thing as before. We introduced another hidden layer here. And for the NOT, we are going to connect this one here with a negative weight. And here we have to use a negative bias as well. If you're going to use a value of minus 0.1, it will work, because when this is on, so a value of 1 multiplied by minus 0.1, so we do get here minus 0.1, and it's not greater than minus 0.1. So when this is on, this is not going to be on. But when this is off, then that's going to be 0 times something, which is 0, is greater than minus 0.1. So basically, we have a way here to get the opposite of this node. And that's why the green area is appearing here nice like that. And there's no overlap or anything going on. Like if you remove the gray area here, it's clear that the green is the opposite of the gray. Okay, so does it work? Let's restart. Still doesn't work. It's still going too fast there on that section. So we're going to have to cap the speed even more. Maybe minus 0.3, let's say. And let's see what happens here. These were the most problematic things. And the car is going to go now quite slow compared to before. Yeah, it still did a little bit of a loop there. But it's not crashing anymore. So maybe even a smaller speed. Minus 0.2. Let's see if it crosses. No. Okay. It doesn't cross the line anymore. So with this logic, the car moves relatively slow to what it can do. But if you think about it, and if you would think that these are real cars and you're watching them from the helicopter or whatever, they would look like that. They wouldn't speed up crazy like what we had previously. So this is really a decent speed for a car inside of a city. So we did it. The car can now navigate these complex situations. It's even going on its own part of the road. And maybe it's a good time I show you these other buttons up here so you can save the current car network structure that we have here. We put a lot of work into this, so maybe we don't want to lose it. And saving from this button, and you can also load from this other button. So you can try different configurations, save them under different names, and then load them to see how they work in different scenarios, which, by the way, you can load from this button right here. So if you took the virtual world course, you have the editor there, and you can create any world you want for the cars to drive in. And you can use this playground to load those worlds into it and see this car or any car you build here manage it. Now, one thing that I still want to show you is that the network here doesn't look like the one I showed you in the very beginning of this course. Like if you type here default, the network here is quite different. It has just one hidden layer, right? And then this right sensor is connected to something here and to something there, not directly to these outputs. And there are significantly many weights here on the right. This is the common structure neural networks have, really, and the reason why everything on this line is connected to everything on this line, and here the same thing, has to do with how neural networks are represented internally as matrices and speeding up some of the operations and also a few other things I'm not going to get into. But basically, we could convert our network into this network by just adding 0 weights where they are needed and making this kind of relationship here so that this node is in sync with this node and so on. The problem is this one more hidden layer is missing here, so how can this car do something here? And let's go back. I can show you that we can actually remove this node from here as well. So right-click on it, connect like this, and just put here the 0.1, 0.1, 0.1. So now we have that gray area here, but it's covered by the green, so we can't see it. And the green has to be a knot again, but somehow created without that extra node from there. So we can connect this as such, put a negative 0.1 here, a negative 0.1 here, and it's not quite right here. This needs to be minus 0.2. I'll let you do the math for this one. But you can see the end result is exactly the same, and we didn't really need another node there, another hidden layer. Now, you may want to save this version of the network as well, because it's different than the previous one. And what I'm going to show you next will kind of destroy it. So focus on this network here and change the URL to str_3. And notice that it looks different, but it's really the same thing. It's doing the exact same things as previously. Like you can recognize this shape here and adding on these other two, you can see them here. Whatever network you create in str_2 is going to be converted in this kind of full network that you see here. And these weights are essentially zero, all of them that are added new, and you can recognize the other connections there. Plus these new nodes, 2 new nodes that are needed to connect to the turning right and turning left. And they are just in this kind of synced relationship. So whatever the node here is, this one at the top is doing the same. And this network looks much more like the one on the first page there. But that one had also some values for these weights. And the reason why that is that I optimized this network a little bit more by using the genetic algorithm. So I did this. I lowered the mutation here. And I tried to generate cars that are very similar to that one, but a little bit different, so that maybe they act better. And this is really slow. Maybe it's acting a little bit better if we put this to the max. But basically, this is really slow because it's trying to process this larger network and do these visualizations. And yeah, but you can see this car that is leading here, the one that covered the most distance, is not the one that we previously had, that we were previously working with, because it has some values for these other weights. It might crash at some point, I don't know. But it's at least a car that is going, for now, better, faster than the previous one, the one we designed. And I think I saved one of these cars and I've used it as the intro there. You can see some of these connections here are still quite obvious that that the network is based on what we designed, but there may be some relationships between these nodes that we didn't even think of, and this network is potentially finding some of those. It's also making this much harder to explain what is going on. So this is the truth. Whenever you optimize using automatic methods like this, you will start to get a network that you can't explain every single thing from there. Usually you can't explain anything from there. But in this one, because of all the things that we have done, we do still have some idea of what is going on. Now, this car seems to be doing quite a good job. I'm going to save it. And let's close this and see it going. And it might be faster, but it's not as smooth as what we had previously. It's doing this kind of fidgeting here. Sometimes it's pressing acceleration and brake at the same time. But you see how these small changes in the weights are affecting the overall result. Even though it's kind of doing the same thing, some of these structures are totally different. So here, there is not anymore that kind of separation. The gray area looks different. It's doing an or here now. It's not doing an and anymore. So probably, yeah, this bias here has been made lower. So this is interesting, an interesting change. And the green region is very much the same as before. So now this is not anymore when not braking, when not accelerating, you brake. It's also these two sections appearing here where both of them are pressed at the same time. And there's much more going on here. Like when the car is turning at some point, I noticed that the green region is, you saw that? It was changing a little bit. The other sensor is somehow interfering with the logic from the component that we had independent previously. And there might be some good reason for that. Like if you do see that it's empty on the right, maybe you want the car to brake because you don't want it to go crazy, even if the front sensor is not doing anything. So it is possible to come to some better logic, more complex logic, automatically like this. And here, this thing here is really strange. Before we just saw the clear separation between blue and red, and what is this thing? If we remove the red, you can see that this is actually blue appearing here. So the blue somehow makes this shape now. And it depends on the speed as well, if it's going to act like that. So depending on the speed, this steering left, which we only use to correct its direction, has a different effect. Hopefully with all this you can see that we can still understand some of the things that the car is doing, even though the complexity has grown, especially because it's based on something we created, but also because of the tools that we are using here and the understanding that we gained during these lessons. It's important to remember that this is a small network. I mean, compared to that deep neural network we had in the machine learning course, this is nothing. And the one there is nothing compared to powerful ones out there. So just imagine the complexity those can handle if ours can already do so much. And by the way, in case you're curious, I did teach how to implement that chart and the decision boundary plot in the machine learning course. The diagram that we're using here is that, but regions can also overlap because of what I said earlier. Multi-class, multi-label, remember? The car is now moving nicely, staying on the right side of the road and navigating this maze quite well. But what will happen if we add some markings? Well, nothing. The car has no idea they're even there. We need to add more sensors and update the logic for them as well. The new network will have 5 inputs this time, so get ready to navigate in higher dimensions. Start the playground from the link in the description, and you're going to see this scenario, which is pretty similar to the last one, but it has also these markings on the road, like the stop marking and the traffic lights. Now, the way we're going to solve this problem is the car is equipped with 2 new sensors. They are not really visible here, but if you're going to turn on the manual override and go forward like this, you're going to see that this red sensor appears here. It's overlapping the other one. The way I implemented this on top of the code from phase 1 is I just added a stop sensor, another sensor to the car, and it has only one ray here that is casted in front. But it's looking for borders from these markings instead of the road. One other thing that I did is the car is only seeing this border if it's looking at it from this angle. Like if I'm going to go up here slowly and look at the stop like that, it doesn't see it. It doesn't turn red. You could model this logic in the neural network as well, but that will make it even more complicated, and you'll see today it's going to be quite complicated by the end. Now let's go back here and see the input node associated with this sensor. So it's this one here. It works pretty much the same as the front one, but it's the distance to the stop marking there, not to the side of the road. So you can see that value changing like this, and it's 0 if it doesn't see anything. Now for the traffic lights, the same thing, but a different input node, a different sensor in the car object as well, and you can see those values changing. But if the traffic light is green, then this sensor is not reading anything. So it only looks for yellow or red traffic lights. And the same thing applies as before. If you're looking at some traffic light from the wrong angle like this, then it's not going to trigger anything. You need to look at them from the correct angle, like this, assuming that you're driving on the right side of the road. So 2 new nodes here. And stop to think about it. when we had one node, we were using that to define a line. 2, they were defining a plane. 3, we had this hyperplane. What are these? Well, they're also called hyperplanes. Anything after 3 dimension is just hyper. But visualizing or understanding what is going on now when we build this new network is going to be much more challenging than anything else, because we are not anymore in the 3D world that we are used to. So let's start solving this problem, and we're going to start from scratch. I'm not going to load any version of the car from previously, because I think recapping what the logic is helps to understand how we complement the logic. So we will build the same car that follows the right-hand rule of solving mazes as previously, but a little bit different. You'll see. Let's move this sensor for detecting the right side of the road there, and the turning left and right. Let's get them out of the way for now. And here, let's focus on moving forward and stopping. We're going to focus on moving forward, actually, and for that we need the forward sensor so that we can detect when the car is going to stop, and the speed so that we can control stopping at different moving rates. Now, let's create a new node here, like this. And 2 more, one like this, and one like this, and one like this. You can probably tell something crazy is going to happen. But we begin with the very basic logic here. So let's define this weight to be -1, -1, and this one was -90%, like this. And all of these weights here, I'm just going to put +0.1 so that this node just, whatever it is, it's going to sync with this node, and this will sync with that node, and this will sync with that node. So the logic here is really simple, what is happening here. Whatever this value is just transfers to all the other ones. And you can see here on this axis that just means the car is going to accelerate until it's very close to the border. So like if we are going really, really close to the border, then it doesn't accelerate anymore. And this line moves here when the car is moving. Oops, I crashed it. Let's restart this. The reason why that line moves like that is because of the speed. So because this is still a 2D scenario, we can put here this one like that and see the decision border here. So now the car should be able to go forward and stop whenever. Oh, it's gonna crash because I didn't connect the reverse. So here we are going to do a not. Whenever this one is on, this will be off, and vice versa. I'm just going to put here -0.1 and -0.1. And if this is off, 0 multiplied by something is 0, it is greater than -0.1. But if this is on, then -0.1 is not greater than -0.1. So this node, whatever it's going to say, this will be the opposite. And now restarting, is going to stop like that. And I'm not going to bother with this kind of blinking here because it's not possible to solve without doing a lot of redundancy and changing some biases a little bit. But to stop the blinking, because it is bothering me watching it like that, I'm going to press this button for the manual override. And now it's going to stabilize to some position there. And let's do the steering logic next. So basically, in this situation, it shouldn't steer because it sees something on the right. So let's change this here to show this sensor pointing to the right and connect it to steering right. I'm going to put here -1, and here a good value was -0.9. So at the moment it's not steering to the right, but if I'm going to move the car a little bit in front, then this point here moved in that reddish region, so that means that it does want to steer to the right. And it's going to want to steer to the right a lot, like that, and eventually it's going to crash if we don't teach it also to steer to the left as well. And we solved that by filling the remaining part here with blue, so it was like this. Now let's restart this and turn off the manual override, and the car is shaking a little bit like crazy there. But it is kind of steering, except for this crazy thing that happens because, let's see this again. Because now it's just speeding up and all of a sudden it found out it has to turn. So the speed it had was so much that it made it jump to the other side, and then it got confused. So our solution to that was to cap the speed, to make it go not as fast as it can, but at a reasonable speed that the sensor is enough to solve this problem nicely. And we did that by doing this, adding a new node here for the speed. Let's change this to see what's going on, and I'm going to remove the blue and red so that they are not confusing. We have to cut this gray plane here like that. And the good value for this was 20%, so I'm going to put this to -1, and here -20% like this. And this was now connecting here. Let's just remove this, set this weight to 0, turn this one to on to see how it looks like. So 20% means that from here. And we want to combine the two. So not like that. This is now doing the OR. So it's either below this slanted line or below this section. We want to combine them so that we get the intersection of the two. And we can do that by increasing the bias here by 0.1 like this. Let's stop also that fidgeting here, so we can put -0.89 for the turning right, and that's going to give a small gap here for when turning so that it doesn't correct its location all the time like that. Let me show you. Here, if we put the sensor to the right and turn on the other two colors, and we really need to use high resolution here. Let's take off also these other things. It's still not very visible, but a gap like this appears there, even if it's -0.89. It's a small gap that prevents it from fidgeting like that. Okay, let's put this back here because my computer is starting to breathe heavily, and turn off this manual override, and now the car should be doing very nice things here. Let's have a quick check to see if it's turning properly and if it's visiting all of these regions as well. Everything looks nice on the right. Yeah, turning properly and not crossing the border. So this is exactly what we had last time, but the extra nodes that we have here are to help with the new logic that we are going to create for the stop marking and for the traffic lights. Yeah, some what should happen now is that the car should stop at the stop marking, not just cross there like it's nothing. And the way we do that is the same way that we stop at the road border. Like, we are going to copy this logic for the stop node here as well. So let's try to do it. This is -1. This is -1. And this is -90%. Like that. And now let's investigate if this works. We're going to put here the speed, like so. Let's not worry about turning anymore and just keep these gray and green regions there. I think it's actually clearer if we keep just the gray region, because the green one is always going to be the opposite now. So here, with the gray region emphasized, we look what happens when the car is reaching the stop sign. And let's turn on the manual override here. So when it's reaching the stop sign here, we still have this front sensor telling us that it's okay to go, because it doesn't see the stop sensor. But if we change this to be the stop sensor, you're going to see that this point is going to be much closer to this side, because the stop marking here is closer than the road border. So let's see that. Right, so this did move like that. But now it doesn't have that region that tells it to slow down. So we have to give that to the end result here. And I'm going to create a new node. I think it makes it clearer like this. And let's just copy whatever happens here on the right for now. 0.1, 0.1, 0.1. And let's disconnect this one. So I'm going to put here 0, or let's just remove it entirely, and connect this one instead. So now we do get that thing here, but we don't get it anymore for the front sensor, because that part is disconnected. All right. Let's still focus on the stop for now and just check if it works. So I'm going to remove this manual override, and it goes and it stops at the stop marking. And it never goes anywhere else from here. So this is something we all have to fix. Let's put on manual override so that this doesn't blink like crazy. And now, because we are stopped at the stop, we want to move again. So looking at this, we would like to have some gray region here on the right. It's okay to move now after we have stopped at the stop. So let's add another link from here. It's only going to be a vertical region. It doesn't depend on the speed or anything like that. When we are really close to the stop marking, it's okay to go. So we can set here a value of +1 like this, and a value here of maybe, let's try 90%, so that this part from here, 90% from here, gets gray. So 90%. Now this node needs to be connected as well, and we are going to do an OR here between this one and this one, because if this is okay or this is okay, it's going to accelerate. And you can see this region appearing here. It's not capped, but actually we don't have to worry about capping for now. I think it makes it more complicated. So let's remove this line. And here, instead of having a bias of 0.1, we just have it 0, so that this value transfers like that. And let's refresh to see what is going on. Remove manual override. So the car is slowing down like this, and at some point it continues like that. So it's great. It crashes there, but the logic from here is going to prevent that. It's going to do the capping and everything. Now, it's up to you if you like what happened with the stop. I think that it actually took a little bit too long. So maybe a value of 85. Let's try 87. I think this is now growing too much. I don't want it to be a full stop and to wait seemingly so long there. So I think this is decent how it looks like. In the real world, a stop should mean a full stop, checking if other cars are there, and if not, you can go. But I like things to be a bit faster here. And speaking of other cars, in the demo I have on the website, cars give way to other cars on the right. That works with another sensor like this. It looks fancy, but they're just a bunch of rays in front and to the right that check for cars. If any of them sees something, a sixth input is used to make the car stop. We won't be adding more cars here because it's quite messy, but we will do the traffic lights logic. And that's exactly the same. Think about it. Waiting for a car to pass or for a light to change is the same thing, really. Just the sensor is different. We'll move on to the traffic lights in a moment, but first let's reconnect this side so the car doesn't crash like that. I'm going to replace this link from here to this node in the same way. Nothing changes really. So that I can move this one here on this side and connect nicer to this one. Here we have to do an AND. So both of these need to happen for it to work properly. Let's restart, and we can see now how this looks like combined with the cap there. It's slowing down at the stop and now moving to the right. And now as it's moving down, let's change this back to the up arrow, which doesn't have that special part there for accelerating again, which would just make it crash there. But you can see that it's slowing down and it's doing the turn properly. So both logics are combined now in a proper way. It's good if you stop and play with these values, try to inspect things and get your own understanding of this before moving forward. But the last part here really is going to be quite easy. It's a trick that we're going to do to make the traffic lights also work with as little effort as possible. For that, we are going to move the traffic light here in the middle and the stop to the right. And the traffic light is just going to connect to this node with -1 here. And just like magic, it's going to work. Let's have the car go back to the starting point and see what the traffic light is showing here. You saw it was slowing down and wanted to stop, but then the traffic light just became green. So basically what we want the traffic light to do is like the stop, but we don't want it to start all of a sudden while the traffic light is still red. It's going to stop there and wait there until the traffic light turns to green by itself. So that's the logic. It's actually a simpler logic for the traffic lights than it is for the stop, even though you think that these are more complex. It's the traffic lights themselves that are complex, not the logic that the car is doing. Car just stops. And this is a little bit cheating because I'm assuming that there are no traffic lights and stops next to each other. So that's why this logic works, but it works in most cases, so I'm happy with this. Now, the logic here, this OR and this AND can actually be simplified, so we don't need these hidden layers. I'll show you. Let's remove this node. And car is, wow, it's doing some crazy things now. And connect these ones here as well. So everything connected to this one node there. Now, this is a value of 10 and this is 10. Let's make this one 30. 30. And this one here, let's make it 60, because we're gonna put these weights here to 0.1 and 0.1. And if only one of these is on, it's enough to turn this one on. So we are essentially doing an AND here combined with an OR somehow, with one single neuron there. It's interesting, but it does help to simplify this. And if you restart now, it doesn't work because I forgot this bias here. So now I just want to transfer whatever is here to here, and this bias has to be 0. Okay, so now it should work exactly as before, but with a simpler structure here. We can also get rid of this node. So if your goal is to have less hidden layers, we can do that like so, and connect this one here, and this one here, the minus and the plus. And it's the same logic as before. Let's just check it. And you may wonder, why is this moving here? Well, it's because there are other things, there are other sensors appearing on some other axis. So now this slicing here, it's not anymore a slicing of a cube, it's a slicing of a hypercube. We have not just one more axis, the forward sensor. We have the forward sensor, we have the right sensor, we have the stop sensor. All of them are there somewhere. And here we are just visualizing a slice of that complex hypercube. And you may see some of these movements happening there from time to time. But yeah, you can actually get rid also of this node and simplify this even more. So you could connect all of these directly to that and all of these directly to that and figure out how to do here the knot by a combination of links like that. I'm not going to show you that. That's going to be your homework. But it is possible to simplify this even more so that you need only one hidden layer here. But in my opinion, the logic that I'm reading now is actually clearer for me, for a human, to understand. So I can definitely understand here this kind of compound operation that is happening. Like this will turn on when it's greater than 0.6. These two will make it 0.6 exactly. It needs something else. And these are not enough to get anywhere close than that. So this logic here is clear. It needs to have both of these and one of these. So it's actually even simpler than having the more nodes there. And here we just transfer the value here and not to that. If I'm going to have all of the connections copied to the other one, that's just going to make more math in your head. But here the not is very easy for me to understand. I don't know about you. Please keep in mind that we are not really solving self-driving here. This simulation is very simple, and these markings in real, we don't recognize them so easily. I mean, we could, like road markings could send signals and smart cars could pick those up, but that would be very costly to maintain, so car companies have a different approach. They make cars see the world as we do, with a bunch of cameras. They have good reasons for doing that. The roads were made for us, so seeing the same way we do should be enough to solve self-driving. But that gives another layer of complexity here. Large neural networks are used to look at the scene like that and figure out that there is a stop sign there. Not too different from the drawing recognizer we built in the machine learning course, where to get the best accuracy we used a monster of a network. And there we didn't get to 100%. No big deal for the drawings, but here we kind of have to, right? Luckily, stop signs look the same everywhere, so Never mind. Anyway, the problem is far more complex, and we're simplifying a lot, is all I'm trying to say. We have a nice car now, going around and obeying all kind of rules. But the car just goes around forever. Usually they go somewhere. So we'll experiment with adding a kind of a compass sensor that tells where the target is. Now, spoiler alert, this compass approach is not great. So I won't insist on it too much. I just want to get something that kind of works, so you see it's not enough in practice, and why we'll need to study pathfinding algorithms soon. Speaking of which, I'll have to show you how to update the self-driving car codebase to load the cars we make in this playground, and also how to get it ready for pathfinding. About time we get back in the code saddle. Start the playground from the link in the description, and you're going to get this scenario that also has a target. The car has 3 sensors this time because we're going to teach it to turn left or right depending on where the target is, so it's going to need to see on the left as well. And there is another sensor that is not really displayed anywhere, but you can see it here as this node. This value here tells the angle that you need to turn to face the target, kind of. It's not really an angle, it's again a value between 0 and 1, but let's check it out. So I'm going to turn on this manual override, and hovering this, you see there a value of -24. This just means that you have to turn left. Minus means left, and positive values mean you have to turn right. So now you have to turn right 25%. And then you would be facing this. So a 0 value means that you're pointing exactly at the target there. And if you're going to go all the way like opposite direction, then it's going to say -1. But as soon as it's more convenient to turn right, you're going to start getting positive values there. So 1, essentially. And it's just telling you that now the car should turn right so that you turn to face the target. That's what this sensor says. And really, it's kind of like a compass. If you look at a compass, then you get the same information from that as well. Many devices have these kind of magnetic sensors nowadays, including smartphones. Okay, so with this setup, let's try to make the car head to that target. And I'm going to start by cleaning everything, and we're again going to work with some components here, like last time. So let's move now this up sensor and the speed sensor here, and put the reverse in this top left corner, and now turning left, turning right, and it's going to use these sensors here, the left and right sensors, and it's also going to use this one, but let's set it aside for now. The logic we'll implement here is going to be really easy. I want just the car to move somehow and control the steering based on this other sensor. It won't be anything nearly as polished as what we did in the last lessons. I just want to give you the idea how you might do such a thing. And let's do the simple logic for moving forward. So let's focus here on the speed and the forward sensor and make that slope appear there. So -1 and -1, and here we're going to set -90, and this is going to be just the opposite. So I'm going to put here +1, +1, and positive 90%, like that. Now if we restart and turn off the manual override, we should see the car going there and stopping like that. Good. I'm going to turn back manual override and move the car down a bit like this. And let's implement steering with a similar logic as here. For that, I'm gonna put here this sensor and here this sensor, so we are focusing on that, and let's connect this one here with a -1 weight and a +1 here this time. And now here we are going to use +1 and -1. So we get this very simple looking structure here. And what this does really is, now the point is here, so the car wants to turn left. And it's essentially trying to balance out the ratio between these. So the end result is going to be that the car wants to line up in the center of the road most of the time. Let's try to see how this works. So the car is in the middle of the road, and now these are equal, so the car doesn't decide to turn at all. It's really perfect here how equal those values are. Normally you don't get something like that. Let's turn off this gray and green so that there is no blinking happening and see this again. All right. And now let's see what happens if we add a bias here. So we're going to add a bias, maybe 20% here for this one, and -20% for this one. And this is going to mean that the car wants to turn right here, and it's going to prefer the right lane, actually. Let's try to restart. And now you see the car keeping the right lane there, and then at the intersection, it's steering left because of its initial position when entering the intersection, its acceleration. And actually, at the intersection, if you look here, this point is somehow going a little bit crazy. But anyway, this kind of configuration means that the car tends to turn left at the intersection and not right. And if you do the opposite, like put here -20 and here +20, then the car wants to drive on the left lane, and here at the intersection what's going to happen is that the car is going to turn right in this case. And it actually does a pretty good job even with this very simple logic here, but fails at the end because this proportion here tells it to turn left. Anyway, this is not important. I just wanted to get here some logic that actually works and decides how to turn at the intersection, currently based on these biases. But we're not going to use those. We're going to use the value of the sensor instead. So I'm going to put here 0 and 0 as we had before. And let's move this one here because it's somehow a natural place for it to sit. And here I'm going to connect this one with a positive weight, let's say 20, and a negative weight here like so. And look what happens here. I'm gonna turn on manual override, refresh, and now I'm going to move the car somehow here as center as I can. There. It's not fantastic, but anyway. And you see, this falls into the red region now because of how this target is influencing. The car has to turn to the left, so it needs to now turn right so that it's on the right lane for that turn to work. So if I'm going to turn off the manual override, then the car is going a little bit to the right and then is able to manage that left turn. But if you change this link to TGT_1, then there's a target on the right, and the car is already doing crazy things there. Let's see this again. So the car turns to be on the left lane and prepares for the turn to the right, And then it continues to do some things here, and it is affected somehow by this target still. Like, you can see that it starts on the left lane, but after passing this, it moves mostly on the right lane because now the target is on its left. So it's still preparing to turn left to head back to the target, but it never gets another intersection to try. Anyway, this does work to make the car turn in different directions according to where the target is. But it's not always a good solution. Like, if you go here and put TGT_2, you see the target is now on the left. And the car is going left at this intersection because it's where it thinks the target is, but it has no idea of the road structure here. So this is a big problem. We either have to teach this road structure to the car, make it part of the neural network somehow, a lot of inputs, weights, biases, very, very complex stuff, or rely on some other solution that gives us the path to follow. Go up here and type S is equal to SP for shortest path. And you're going to see very different things here. This logic is not the one we were playing with now. It's actually the one that teaches the car to do the right-hand rule that we played with previously. And that target, the compass sensor, is completely gone. So the car is just exploring here, this maze, and nothing else. But there is this added button here that tells the car to follow a specific path. And let's try restarting this and pressing this button. And it's going to obey now this corridor that appeared here. So these lines here that you see are going to be new borders that the car is going to try to listen to. This corridor is the shortest path from where we press the button to where the target is. And you can actually remove it and press it anytime you want, like now, and see what the car is doing. We just told it, go to that target, and it's doing it. It's going to that target no matter where it is in this maze, so to speak. I'm going to teach you how to implement this algorithm for finding the shortest path between 2 points in a graph. But for that, we need to take this brain back into our code base from the end of phase 2. So we're going to need to set things up a little bit there, and in the next lesson we're going to implement Dijkstra's algorithm. This part is mostly for those who followed along with coding the self-driving car simulation and want to get the full connection here. If you just want to learn about Dijkstra's algorithm, you can skip this part. I'll post the new code on GitHub, and you can take it from there before the next lesson. This is the code from the end of phase 2, and index.html looks like this. There are many cars there in this simulation, and they're trying to navigate this more complicated world. The best one is always highlighted. Now, the first thing we want to do is bring the logic for the right-hand rule here inside of this system. And we're going to go to the code and create a new folder here. We are going to name it saves. And in it, I'm going to paste the car we saved in that one lesson. Mine looks like this. And if we open it, we can see a lot of different things here. It's basically JSON information, and it's stored inside of this car info global variable. The only important things here really are the max speed, the acceleration, and the friction, because they have different values in the playground than in our code base. But also the brain, let's see where that is. Not these, but that one. So the levels, the inputs, outputs, biases, and the weights, we have to load these from here now. And the sensor is also important. Like the car here has 5 of these ray casting sensors. We have to use just 2 of them at the right angle and with an offset. This system doesn't yet support that, but it's an easy fix. And we have to include the speed of the car as well, right? So a little bit work to get this to work exactly like in the playground, but it's not very complicated. The sensor values are here as well. This ray count, ray length, ray spread, and the new offset. So let's go back to index.html here and load the car just here beneath the world. So it's going to be included like a basic JavaScript file, right-hand rule.car. The extension is just to mark that it's a car file. And let's save this and go inside main.js, close this, and go to the place where we generate the cars. So there is this generate cars function down here. And we want the car to load the information from inside of that car info. I'm going to say here car is equal to, and let me copy this from here. I'm going to cut it here. And this is going to be what we push inside of the cars array. But before that, we will say car load the car info like this. And this load function inside of the car object is what we need to implement. So we go here, and below the constructor, we just have to type load, given some info. Let's set the brain to info.brain, and those properties max speed, info, max speed, friction, info.friction, acceleration, info.acceleration. And the ray count from the sensor, from info sensor ray count. And we have to do this for the ray spread, length, and offset. So I just copied this 3 more times, and this is going to be here ray spread. Let's copy it here. Ray length. Let's copy it here. And array offset here. And this offset is something that the sensor doesn't support at the moment, so let's fix that real quick. They are all made to be symmetric at the moment. So here I'm going to say this array offset is equal to 0 in the constructor by default, but it can be assigned something else if we load it from that file. And when we cast the rays, this is the important part, we need to add that offset to each individual ray angle. So here I will say plus this ray offset. And we're almost done. The last thing we need to do is set the speed as the last input to the neural network. So in car.js, where we update here, we get these offsets as inputs, and that's just fine. But here we also have to add the speed at the end, and we can use .concat, and it has to be an array that we give here. It's going to be an array with just one element. So the speed, it's going to be a normalized value of the speed. So we take this speed and we divide by this max speed, so that it's going to be between 0 and 1. And if we save this and test, we can see here the network working. It's the same thing that we have in the playground, but visualized a little bit differently. You can probably recognize here the weights and the biases, how they look like. And this is the speed value that we have in the right, and these two are the front and right sensor respectively. And it's doing that right hand rule now. But one thing that you might be curious is, where are the other cars? So we see that all cars are loading this car info. They have the same brain and they are actually overlapping in the simulation. Now here we do have this code that is doing a mutation, but it needs to have something in local storage for it to work. So if we go back and save this car in local storage and refresh, we see that it does now some mutation like that, and it actually gets other cars as well, not just the one that we originally created. Many of these can fail depending on the mutation and how much change has happened there, but it is what it is. And you can control the mutation from here if you want, but I think a value of 0.1 is quite good most of the time. Now, to teach the car to follow a path, to do the path finding, we will have to create a world that has a target. So we're going to go inside of the world folder and open this index.html next. This one should show empty like this, and we're going to start clicking to create a graph that is useful to teach about pathfinding. Now I'm going to start clicking here, and it would be good if you try to follow the same kind of structure. If not, you can also get this world from GitHub. But basically, I'm going to start here like so, and let's zoom out a little bit. So here, if you haven't followed the previous course, we just click to add points and zoom out and use the middle mouse button, the one with the scroll wheel, to pan around. And after doing this, we can create now a few more points. So maybe something like this. Let's also add a new point somewhere here on the right and connect this one back to the start. Now right-click to deselect this point, and clicking to select this one, let's add a link also here, and a few more of these segments up here, like so. So this should be complex enough for teaching about pathfinding. And the starting point is going to be here. So we select the car and we click here at the bottom somewhere where we want the car to be in the very beginning. And the target, this one, is going to be all the way here at the top, somewhere here, like this. Now, when saving the world, it's important to choose some good position to start at, and maybe the zoom level. This will make some things easier later on when testing. So maybe something like this is what we're going to see at first. And let's save this. I called this pathfinding, and you can find it here, pathfinding.world, in the saves from the world folder. So we have two different saves, one for cars and one for worlds here. Now, to load this new one, we go to the index.html from the root, not inside of the world. So this one. And here, instead of including this big world, we are going to make a copy of it so that I remember that big world exists, and include the new one. So pathfinding world. Now, if you save this and go to our car simulation and refresh, you're actually gonna get an error. Turn on the developer tools and you'll see this kind of errors here. And the reason for these errors are here in the way the world was saved. So pathfinding world is just a JSON object, but big world has world is equal to world.load, and inside of that function we have the JSON object. And it ends with this parenthesis and semicolon. You could add these manually to that, but I'm going to teach you how to make the world editor to save in this format because it's more useful, I think. So inside of the world project, we open index.html and we look for the save function. So the save function is here and it just writes here the stringified version of the world. We are going to change this a little bit. So we are going to say here like this. And now we stringify here like that. And then we close this. And now save this file, go back to the world editor, refresh, and press save again. Overwriting the file is just fine. And if you look now at pathfinding.world, it does start like that. So we made this so that we don't have to do any manual editing anymore like what we did in phase 2. And if we go back here and refresh this page, we can see now the cars going in this new world. But before we check things out there, let's also fix the load function inside of the index.html from world. So what we need to do is go to the load and here prepare to cut out the extra strings at the beginning and at the end there. So I'm going to go here above this JSON data and I'm going to take the JSON string first from this file content, and I'm going to take the substring like so. And starting at the index of the first open parenthesis, +1 because I don't want to include that parenthesis, and then ending at the last index of the close parenthesis. So basically taking the same thing that we had previously. Otherwise, loading worlds will not work with this new format. We just need to take this JSON string and put it here instead of the original file content. Now, if you save this, go to the world editor and refresh. Now load, for example, the big world that we already had there. Something crazy happens, so it's still not perfect. If you zoom out and go down a little bit, you can actually see that that other world is there. But if you open the console, you'll see that there is an error happening. And this error is because after this world is loaded, it's set into local storage. And that part fails. This world is too big to fit into local storage. So we're going to implement the same solution we used to load the world in the simulator. Let's remove entirely this load function from here. And at the top, I'm going to also remove this button for loading the world. Instead, we are going to go at the bottom and add a new script from saves big.world. And this is going to load the world in the same way that we had previously in the simulator. But we need to take out from here these attempts to read from local storage. So all of these things can be removed. Like So now if you save, it works. But there is one small problem with the code, and that is that the roads here at the roundabout are supposed to be one way, and there is a mistake I omitted last time. So to fix it, we have to go in world.js here and see where the loading is happening. So here we load the graph with this function, and this is where the problem is. So we actually have to open math, graph, and load. And here the segments are just loading what is P1 and P2, but not also the information if this is one-way road or not. And we can fix that by typing this here and saving. Refresh, and you're gonna see that the lines here look different because they are supposed to be one-way segments. It's a small thing, but really important because I'm gonna teach you about pathfinding, and we will have to take into consideration one-way roads as well. Now, maybe we want to have a target in this world as well, to have a more realistic scenario. This is my hometown, after all. So let's add the target here and figure out a nice zoom and center point, maybe here where the car is, and save this new world, big with target. Let's go to the index.html from the root, so not inside the world anymore, and add a way to include that one as well. I'll comment out the pathfinding for now, and this will be big with target. Save and go to the simulation, refresh. And now it's loading the big world, hopefully with the target. Let's see. Yeah, you can see it there in the top right. Okay, so this is what we're going to be using to study about pathfinding, but we will work with this pathfinding world to begin with. It's easier than the big one we just created, and helpful when explaining how the algorithm works. So let's make sure we have it here, and also loaded by default in the world editor. Let's add these other ones for reference. Save and refresh, and seems to work quite well. Dijkstra's algorithm for getting the shortest path is really important. When I was at Microsoft, I used to hear about it every day. Now, it's not strictly speaking an AI algorithm, but when added to an intelligent agent like this, it makes it more intelligent because it can find its way to any given location. So I like to count it as one. We will implement the algorithm for calculating the shortest path in the graph object, which is in world.js, and then math, and the graph is here. Now this file is pretty big, but it's just a graph implementation. It has points and segments, or nodes and links, or vertices and edges, depending on the terminology you want to use. I call them points because this is a spatial graph, and the nodes do have physical locations there, so I prefer this terminology in this case. And all these functions are not really important for us at all because they are for constructing the graph, adding, removing points and segments and things like that. The only method that we will use is this get segments with point. So given a point in the graph, we will get all the segments that are connecting to it. And below this one, we are going to start to implement our algorithm. So get shortest path between 2 points. So let's call these start and end. And this method is going to create a path in this path array. And to debug, to see how the algorithm is progressing as we are coding, I'm just going to add to it the start and the end and see if we can make these light up in the interface. Let's return the path, save the file, and we are going to be modifying the graph editor here to also display the shortest path. So let's open this one, and all the way at the bottom in the display method at the end, we are going to calculate the shortest path on the fly. So path is equal to get shortest path between 2 points. And I'm just going to take out the graph point of 0, the first point, and the last point. So graph points of this graph points dot length minus 1. This is just for debugging a first version here. Now let's display these. We are going to loop through every point of the path like this and draw it on this context, the canvas associated with this graph editor. Now let's save and open the index.html from world, not the one here in the root folder, the one from world here above this one. And it's gonna look like this and doesn't seem anything special, but if you look closely, this point here is darker than the other ones. Let me zoom in a little bit. You can see it's clearly darker because it's drawn twice. We are also drawing it now, the start and end locations, and this is the last point that was added when constructing this graph. So this is also darker. But let's mark them a little bit better. We can add here, for example, a size, maybe 50, and let's give it a blue color as well. And when you refresh, you're going to see this much clearer here, and the endpoint is now there. So the algorithm works by expanding, starting to expand here at the start point and growing and growing and growing until eventually reaching the endpoint. Let's start this expansion from this start point and see if we can get to this other point here. Going back to graph.js, and here I'm going to get all the segments that are connected to the start point. In this case, it's only one there, but there can be more. So segs is equal to this get segments with point, the start point. And that's this method from here. And looping through all of these segments like this, I'm just interested in the other point, the point that is not the start point. So let's take it out like this. Other point, we check if the first point of the segment is equal to the start. And in that case, we return here P2, otherwise P1. So whatever start is, we get the other point. And let's add this one to the path and see if it lights up. So path, push, other point. Like this. Let's save this and refresh, and you're gonna see here both of these lighting up. Now, when we have traveled from here to here, it's important to keep a note of the distance that was traveled. because eventually we want to get to the endpoint there and we want the shortest possible travel distance. So the distance here is just the length of this segment in this case. We can go here and say other point distance is equal to the segment length. Simple as that. And now this point knows how far it is from the start point. And after this for loop here, we are done with the start point. We can mark it as visited. We don't need to worry about it anymore. All of the points connected to it have been processed. Now these attributes, distance and visited, we should set them in the beginning. So initialize them to something here. Let's loop through all of the points in the graph. And the distance, we set it to something really large. And I'm going to use the maximum possible value that we can use in JavaScript. So infinity, pretty much. And they are not visited. And now we expanded already from the start point, and we need to choose a new point, something that hasn't been visited yet, and expand from that one. So let's prepare for that and define here current point, set it to the start point, and let's give it a distance of 0, because we are starting from here, we haven't traveled at all, so it makes sense to put this here like that. And you can probably tell that this is going to loop, and this current point will update from start point to something else. So let's change now everything here where start appears to current point, and get a new point to loop this section. And it's going to be an unvisited point. So to keep things clear, let's define here unvisited. And we get that by using the filter method on the points and saying that we want the points that are not visited. We always want to expand the one with the shortest distance that we currently have. So it's also useful to take out these distances. And I'm going to use the map method here, remapping each point to just its distance. So this is an array of distances from all the points. And now to find the unvisited point with the smallest distance, we are going to find inside of this unvisited array the point with the distance equal to the minimum distance from this other array here. So the minimum function expects many parameters here, not an array like that, so we have to destructure it. And then it finds the point with the smallest distance. And this is the thing that loops. So we can try writing here a loop, for example. And let's just loop twice. So starting at 1, going to 2, I++, and everything here inside of this for loop, like so. And if you refresh, you're going to see that these two new points are marked there. And that's because in the first loop, we visited this one, so expanding to process its neighbors. And in the second loop, this one expanded as well. Now, the distance that we are calculating here needs to be a cumulative distance. We need to add what was previously here to the new length of the segment that we are processing in this step. So here I'm going to type current point dot distance plus the segment length, because in the second loop this point here has already a distance, and that is important to be kept, so that this point knows the travel distance from the starting point along this path, and this point now knows the travel distance from the starting point along this path. If you look closely, you're going to see a small issue here, that this point is visited twice. It looks darker because of the transparency. And that is happening with the current logic, but it makes no sense because we move from here to here and then from here to here. So Instead of this point having a distance of 0, which it originally had, it was the starting point, now it has double the length of this segment. We don't update these distances if we find larger ones. So here, let's also not add a point to the path in that case. So if this distance that we are calculating now, this current point distance plus segment length, is less than other point distance, then we do these things. Like so. If you save and refresh, you're going to see that this point is not emphasized anymore, because when expanding like that, it doesn't go back here, it's counterproductive. Let's try to expand more. Let's put here 3 and see what happens. You can see this expanded here. This one didn't expand here just yet, because we only expand from the point with the smallest travel distance that took to get there. So this one expanded, and most likely this is going to expand again and again and again. It's going to take some time until these distances here accumulate to the same value of this distance here. So let's try and see if that's true. Put the 4. Okay. Let's see 5. Growing here again. Let's see 6. Yeah. Let's see what happens next. I think that this distance starts to be almost the same as this one here. 7. Okay, so did this expand or did this expand? Let's see. Aha, it looks like actually this one expanded now, and these are the 2 new points. It helps to understand if we visualize the previous point it was connected to, highlighting this segment. Let me show you. Where we're updating this distance here, I'm going to type other point previous is equal to the current point. And now to visualize these in the graph editor, I can check if there is a previous. There might not be, like for the start point. Then we create a new segment from the point to the previous, and we draw it. We can draw it on this context, and let's emphasize it with larger width so that it's obvious. Save and refresh. And now you can see that this point is connected to this one. So at the moment, it seems like the shortest path to get to this point is from here. But we haven't processed this point yet. This is not yet visited. That happens in the next step. So let's put here 8. And now you can see this update here. And it's showing twice because this point was added into the path array once when visited from here, and then it's updated. It's added again to the path with an update to its previous value here. So a little bit confusing visualization here, but this is correct now. It shows that this is the best way to reach this point. And the algorithm goes on, and it's going to end up eventually to the end point there. So we have to think about the stop condition, and it's not very complicated. We can just replace this with a while the end is not visited. And save, refresh, and now you can see the full path here. But we are not interested in this part from here. We just want to know how to get from the start to the end, right? And the trick is to backtrack from here. So from the end point, we are going to go back, all the way to the starting point. And that will be the shortest path from the start to the end. Let's go back to our code, and we don't need to create the path early on like this. We only do it after this loop ends. So let's remove also adding this other point. Here it was just for debugging. And here we can create the path again, like so, as an array. And let's loop again with this current point. Let's set it to be the end point. And now, while there is a current point, because the start point doesn't have a previous, so eventually this loop will terminate, we unshift the current point into the path. And this is the same as push, but it's putting it in the beginning of the array. So at the end, we're going to have the path in proper order. And update this current point to be the previous. Save and refresh, and you're going to see the path is correctly forming there. And this shortest path calculation is being executed on every frame. So if you're going to change the structure of the graph like this, you will see the path is updating as well. And if we're going to add here a new segment, then this new shortcut is going to be preferred over this one. So it seems to work. But one thing that I still want to do is we have added here these attributes to the points of the graph, and they are things that relate to this algorithm, and we should remove them from there so that other people working on this code, seeing that these attributes exist there, don't get confused. And actually, doing this is not really proper. Like adding attributes like this is not the best practice in the world. But alternative would be to create different structures with the metadata, and that would be just too much work. So this is a quick fix for that. And if you refresh, you will see that it still works, but those segments are not visible there anymore because this previous was removed. Now, we were able to test what happens on different graphs, but we should also be able to test what happens with different start and end points. Testing properly is really important no matter what you're developing. So let's try to add this feature next into the graph editor. We're going to go up where we are adding the event listeners here, and I'm going to add a way to mark a start point and an end point. And we'll do this by pressing the S and E keys on the keyboard while hovering a point. So let's add the event listener for key down to the window. And the callback function, first it checks if we are hovering a point. So like that. And now if the key that we have pressed is an S key, then we are going to set the start to hovered. We're also going to copy this below, and same thing for the E key, and this will be end as the attribute that we are going to store the value in. And now the display at the bottom is going to do here the shortest path, not between these hard-coded values there, but this start and this end. And it makes no sense to do this code when we don't have a start and an end. We will get an error. So we have to do here this check first. Now let's save and refresh. And you're not going to see anything yet. But if I'm going to press, for example, S while I'm hovering this point here, S, and now if I press E after hovering this other one, I'm going to get the shortest path from S to E. Let's see if we put here this as the end point and this as the start point. You can see this loop appearing here. So it seems to work. Let's try also the real world example. So going here in index.html, the index from the world again, and replacing the pathfinding world with this one. So I'm just swapping these here so that I have a reference of what is available. Save and refresh, and you're gonna get this world. But a little bit of a warning here. You can't move points here or add new points, click on this world or anything. You can, but if you do that, it's going to block the interface because this is a really big world, and adding things to it manually, it's a really slow process. So safest thing to do is actually go down here where the world is generating inside of the animate function and comment that part out. When you refresh now, nothing is different, but if you try to add new points to this world or make modifications like drag this point around, it's not going to regenerate everything around it, like the roads and buildings and whatever. And if you accidentally click on something, you don't have to wait like, I don't know, 2-3 minutes for it to process. So let's see, does this work here? Let's say that this is going to be the start point. I'm going to press S, hovering this one. And let's put a destination, an endpoint somewhere here close to the target. So maybe here, E. And you can see it works almost perfectly. The problem is this was the start point. It's going up like that. And then here at the roundabout, this is bad. It's going in the opposite way here. In Finland, you drive on the right side of the road, so it should go on this way. And it's choosing the other one because it's apparently faster, like less distance to travel. This other place looks good, but we need to incorporate these one-way roads here. So these are essentially one-way roads here. You can only go this direction on this one and this direction on this one. And currently it's going opposite there. So we need to do a fix for that. And it's not complicated. We just have to go back to graph.js in our algorithm here. And instead of getting segments with point, we have to get segments that are leaving from the point. So get segments leaving from point, like this. And we need a function for that. It's not available here in the object. So I'm going to copy get segment with point below and rename this one get segments leaving from point, like that. And the logic is going to be quite similar. So here in the loop, if the segment is one way, we're going to have to do something special for that. But otherwise, if the segment allows to go both ways, then this is same as before. If the segment is one way, we have to only push into this segments array if the first point of the segment is equal to point. So if segment.p1 equals point, then push into the segments this segment that we are looping. And if you save, refresh, and now press here S, and let's add also the end location also close to this target as before. Now the path looks like this. It looks proper. So this is how you solve the issue about one-way roads. How was it? Did you understand Dijkstra's algorithm by coding it like this, or do you need a better explainer? Let me know in the comments. I could also teach more about it if you want, like how to make it more efficient or how to use it to compute some other path, like the fastest path, or how to include traffic information, whatever. My PhD was on location-based applications, so you can ask pretty much anything here. Just having the shortest path is not enough. The car needs to obey it somehow. Now, there are several ways you can do it in practice. First thing that comes to mind is to cover the path in targets and have the car navigate to the nearest one each time, using the compass sensor. If these targets are close enough, the problem I showed before goes away. If you like this idea, that's your new homework, because I'm going to teach you another approach. We'll generate a corridor around the shortest path, like that. So the car from earlier, doing the right-hand rule, has no choice but to follow it to the destination. Now get ready to go down the corridor of knowledge. We're going to add the functionality to generate a corridor in the world, because we need to have information about how wide the roads are and things like that. So in world.js and then world.js, below this generate method from here and implement the method generate corridor, it's going to be a corridor that links again a start and an end point. So start, end. And we begin by computing the shortest path between the start and end using the method we implemented before. Now, from this path, we are going to get the segments, the consecutive segments that build the path. So let's generate those in this array. We are going to loop starting at 1 and all the way until the length of the path, and add to these segments a new segment with the point from I-1, so the previous point, and the current point, path of I. And to get the corridor, we're going to wrap these segments in the envelopes. So going here, let's say temporary envelopes, because we're going to unite them later. We remap each segment to an envelope created from this segment, using this segment as a skeleton. So each segment is remapped to an envelope using the road width and the road roundness, like this. And let's just set the corridor to be these envelopes for now. We still have to do something to them, but let's debug so that we know these things are working at the moment. We're going to draw this corridor below in the draw method here, and before drawing the cars, so that we don't draw the corridor above the cars. Now we have to check if it exists. Maybe we don't have one. And then looping through all the elements. These are eventually going to be road borders, so segments. I'm going to use this variable name here to loop through the corridor and just draw it on the context. But both the segments and the envelopes have a draw method, so this is going to stay the same. Now save this file, and we have to generate this corridor somewhere. And we'll do that inside of the graph editor. So in our event listener we defined before, we have to check, do we have here a start and end location? And if so, we tell the world to generate the corridor between the start and end locations, like this. Now, because the world has a way to display its corridor, we don't need this code at the bottom here anymore. And generating the corridor is done only when we press S and E over some points there, so not on every frame. It will be displayed on every frame, but not regenerated on every frame. It's important because generating the corridor is more processor intensive than just figuring out the shortest path. Let's save this and refresh. And now let's press S here, and let's go somewhere, maybe just here, and press E. And these are now the envelopes. Let's try a few more times, maybe E here, S here, E here. Seems to work. But when generating these corridors, we really want to use the car's location and the target location. And the car can be not where the point of the graph is. It can be anywhere, like it's here. And the target can be at a house. So we need to implement a way that the start and end points can be anything along these segments here. And we'll make that work by essentially pressing S and E no matter where the mouse is here, but then projecting the mouse to that segment, and that will be the start location. I'll show you. We go back to our graph editor here, and we don't need to be hovering over anything anymore. So we can do this. And instead of this hovered here, we can say this mouse, both for this one and for this one. Now, of course, we can't use this point directly, so we need to project it on the graph and actually add it to the graph. It's gonna be a little bit work to do, but not horrible, you'll see. Inside of world.js, where we are constructing the corridor, so in the generate corridor method up here, we have to do something to these points before passing them to the shortest path. Let's take first the nearest segment to the mouse click. So we can use here the get nearest segment from the start and looking inside of all the segments from the graph like that. This is going to give us the start segment. And we can do the same thing for the end segment, but using end here. And now we need to project this start point onto the start segment to get a point that is on the graph somehow. We can do a projection using the segments method to project the point like this. Now this here returns two things. It returns the point and the offset, how far from the start of the segment we are. And I want just to use the point, and I don't want to complicate the syntax too much afterwards, so we will destructure this directly to get just the point, and we will refer to this point as proj start. And we can do the same thing for the end, for the target essentially. And now these two new points that are over some segments in the graph, we need to add them in the graph as actual points, and they need to be connected to other points in the graph. So let's do that here, taking the graph points and pushing the projected start, and doing the same thing with the projected end. And now the segments we need to define as well. They will be temporary segments. After we do this pathfinding here, we don't need to have them there anymore. We should remove them from there. We don't want to alter this graph structure forever. It's just a temporary thing that we need to do right now. So the first one is going to be a segment from the first point of the start segment to the projected start. And then the second one will be from the projected start to the second point of the start segment. then we're going to have the same things going on for the end segment and the projected end point. Like so. And the graph segments also need to know about these temporary segments. Now I'm going to append them at the end using concat. Like so. And very important here, when finding the shortest path, we don't use start and end anymore. Instead, we're going to use the projected start and projected end, the points that we just added to the graph so that we can have any start and end location on the road. Now, after the shortest path is found, we can clean up. So let's remove the points that were added. And we can do that with the remove point method from the graph. Let me copy this for proj end. And this is everything we need to do really, because when removing a point with this method, it removes also all the segments that are connected to it. So these temporary segments will be removed as a result of this. Refresh. And now if I press S here and E here, you can see it doesn't need to be anymore on a point in the graph. It can be anywhere, like S here, E here, and my mouse can be anywhere. Like I can press S here and it's gonna map to this point because that's the nearest point from the projection. There is one problem that happens, like if E is here and S is here, you can see this thing. We need to also connect the projected start and the projected end if both of them are on the same segment. If the start seg is equal to the end seg, essentially. So I'm just going to go here and if they are the same segment, I will add to these temporary segments a new segment connecting the projected points. Like so. Now save, refresh, and if you press S here and E here, you can see there's no more that problem, and everything from before still works. But we still need to unite these envelopes to do a polygon union, a union on their polygons. So let's go back to world.js. After we have the envelopes here, we are going to generate the segments, the road borders. Let's say segments is equal to polygon union, and we are going to take out from the envelopes just their polys, because the union method here works only with polygons. And let's set the corridor to these segments now. Save and refresh. Let's press S here and E here. And this is now the corridor, and it doesn't have those kind of artifacts where the intersections are. So it's good, but I want to emphasize it a little bit more. So down where we are drawing the corridor here, we are going to also pass a color. Let's make it red and thicker, like so. Save, refresh, and now when pressing S here and E here, it looks better, I think. The next thing we'll do is close this world project here and now focus on the simulation and make the cars in the simulation respect this corridor. Let's open main.js and close the other two files so we don't get confused. And where we are creating the road borders here, we're going to have to do something different. So first we need to find where the target is. because the corridor will be between the cars, like the best car, for example, and the target, wherever that is. So I'm just going to take out the target by looking through the markings like this, and taking the marking that is an instance of target, like so. And only if the target exists, we are going to take the road borders as the corridor. Otherwise, we just do as we do now, and everything is a border. So if there is a target, let's tell the world to generate the corridor between the best car, which has an X and Y, so it's going to work, and the target center, like this. And now the road borders are going to be equal to taking the segments, the corridor, which is the segments, but we have to map them like you see below there, because the code from phase 1 was working with this kind of structure, not segments that have a P1 and a P2, but an array with 2 points in it. And now else we essentially have this thing from here, but we remove the const. Let's close this parenthesis, and above here we need to define road borders, and I just set them to nothing because they will be populated here. Now let's save this and open this other index.html. And it works. Somehow. Maybe this is the obedient car. Those were just mutated ones. I think this is the one that we created previously in the playground. I recognize these structures here, and it seems to work just fine, going all the way from the start location to the target, exactly the way we want. I wonder what happens at the end. I guess it just starts going back. Let's see. Yeah, it's just going to go back. It doesn't care that the target is there. It just follows the corridor until the end, and there is no end. It's an infinite loop. But this is actually a way to train cars, to get them to be faster or different, because this code also has mutation, and now this one is better than the previous one. This is a different network. It's slightly different because it's doing this fidgeting here. I don't really like the fidgeting, but maybe it has some other components that are useful. So it seems like it is faster than the previous one. And if you think about the racing scenario, then it is better. So this would win. Yeah. And you might be able to increase the number of cars here. Like this is 100. I think that this code supports even more, like maybe 500. Yeah, seems to be just fine. So in the playground, the number of cars is more limited because there are a lot of crazy things going on in the background, and it's using up a lot of CPU. But wow, what is... some crazy things are happening here. It kind of looks like a race already. Wow, that one is speeding up. So somehow it's cornering carefully, but then it was really, really speeding up at some point. And now it's not doing it anymore. I wonder what happened. Okay, now it's speeding up again. Interesting behavior from some of these cars. This one crashed, but it already passed the finish line, so I guess it's okay. I'm already thinking about the game, even though it's not yet a game. That's what we're gonna do next time. Now for the big challenge. Open the playground using the link in the description and try to design the logic for a racing car instead of this obedient one we have now. You can use as many sensors as you want and try it on as many scenarios as you can. I've added several there, but if you have the world editor we built in phase 2, make more of them. It's important to test a lot because you don't know what the track will be on race day. There's a danger your car becomes really good in some specific cases, learning the track basically, but it won't do good in general. So again, remember to test well, and when you're happy with the car, send it over on Discord. Deadline is in May. I'll be done posting tutorials for the racing game around that time, and the live stream will be soon after that. Detailed rules and info about the prizes are on Discord, so check those out and ask if anything is unclear. Thanks for watching and see you guys.